Hello, good morning. Welcome to the day 4 of I3D 2020. So I hope you enjoy our fantastic VR poster session that we hosted yesterday. If you missed it, remember that you have a link on how to access to the poster session right in our website. You can browse our poster room interactively. Unfortunately, there's probably not going to be anybody hanging out because there was quite crowded yesterday afternoon when we had the session. But nonetheless, the link is still up, so feel free to go and browse the posters if you missed it. Okay, so today is day 4 of I3D. This is the schedule for today. We will have our third keynote, which is going to be Julien Pettré from Inria just after this welcome. And then we'll have 2 poster sessions, one on character and crowds, and the other, 2 paper sessions, one on character and crowds, and the other one on capturing the real world. So let's get it started. Just as a reminder that if you haven't registered yet, you can register for free in this link that we have here. It's also accessible on our website. And if you registered, even if we're streaming for free, you get to access to our Discord channel, where you can have internal discussions with attendees of in this conference. Okay, so let's get started, and let's welcome Julien Pettré from Inria. He's gonna give us our keynote today, mostly on crowd simulation. So Julien is senior researcher at Inria, the French National Institute for Research. He received his PhD from University of Toulouse in 2003 and habilitation from the University of Rennes in 2015. He was a postdoctoral fellow at EPFL in Switzerland between 2004 and 2006. And Julien is currently a coordinator of the European H2020 Crowd Boot project, which is dedicated to design of robot navigation techniques for a crowded environment. And he was previously coordinating a national project dedicated to the design of new microscopic crowd simulation algorithms, as well as another national project dedicated to efficient and designer-friendly techniques for crowd animation. So as you can see, he's a wide and very recognized expert in crowd simulation. And today in his talk, he will review the most advanced algorithms used for crowd and virtual crowd simulation. So we are very much looking forward to his talk. As always, remember to post questions for him either on YouTube or Discord. And after his talk, we will have a Q&A where we can have a long discussion with him. So I'll leave it up to Julien. Welcome, Julien, to I3D. We wanted to thank you for being so kind of giving this keynote for today here. So all yours, Julien. Thank you.
Thank you, Dan. Thank you for inviting me, having this opportunity to present this work we've done on crowd simulation at I3D. This is really, I feel very lucky about that. So I hope that you guys don't feel too ironic that we are dealing with crowds today, when gatherings are prevented in many places due to the pandemics. But we'll speak today about crowds. So let me first say a bit about what is a crowd. So crowds can take different meanings depending on the discipline that is considering this as a research topic. So let me first say that we are more interested into the physical definition of crowds, which means that we are interested into the way crowd moves, so crowd can be seen then as a gathering of people with a certain level of density. And what's quite specific as well is that crowd is a place of collective behavior, which means that people act there individually and they have interaction with their environment, with people around them, when the crowd motion emerges from the combination of all these local interactions and individual actions that people have. So this is what we call collective behaviors and emergent motion of the crowd. So immediately you see that I'm talking already about 2 scales minimum. One is macroscopic, so crowd as a whole. So you see a nice example here of what we what we see, considering the crowd as at the macroscopic scale, looking a bit like a fluid motion. And you can also consider the microscopic scale, where it's more about individual motion and individual interactions. So crowds has been for long a topic of research in computer graphics. That's important to mention, and especially because virtual crowds are to be found in movies, in games, or in VR environment, like being presented through a keynote last Monday. And CG is dealing with different kind of problems dealing with crowds. One is to create many characters, so creating the geometries of characters, creating the behaviors of characters, the way they move, how they look, their visual aspects, and so on. And you need variety here, and variety can be quite challenging to achieve. You need also to render many characters at the screen, and it's especially challenging when we are dealing with application to video games where the computational budget is very limited. So rendering so many characters to the screen can be really of a challenge. And more the topic I'm concerned with is simulation, which is to make the characters moving through the simulation. So moving is like controlling their global position in the environment, as well as generating the joint trajectories of characters to see them moving on the screen. So more generally, we can say that CG is concerned by the design of crowd animation systems that deals with those three problems at least, and generally dedicated to the creative industry. So it's not the first time that we will be talking about crowds at ACM I3D conference. I'm so happy to see that there is a full session dedicated to the topic right after this talk. In our team, so we first spoke about our work on crowds at I3D 2009, and then we introduced the crowd patches technique. So let me briefly remind what is a crowd patches technique. It's a way to populate virtual environments in a very, very efficient way, because actually what you see, this motion of characters, everything is pre-computed. So a crowd patch is like a small piece of a pre-computed animation that is delimited, like by squares here in this example, and that you play endlessly, and that you can assemble together. And you can place them endlessly because their content is periodic, and we carefully control the boundary conditions of trajectory so that you can assemble patches together, and characters seems to be traversing those patches endlessly. So it's really generating a limited animation in the sense that you can populate an environment on the fly with this technique with a quality which is guaranteed, because since everything is pre-computed, you can check beforehand if nothing bad happens, such as residual collision with characters also. And this capacity of also populating on the fly environments open new ways of generating a crowd animation, such as by interacting directly with the animation. So on this representation you see here, you actually see moving yellow dots, which you can consider to be characters, walking in sort of a street-like environment. And you can see the user, while the animation is playing, can still edit the geometry of this animation. You can stretch the assembly of crowd patches, and this will update interactively the animation. So you can see the graph, a mutable graph that is capturing this animation, and how you can interact with it, like also cutting, pasting, bending the animation. But let me go back to the topic of crowd simulation, which is really to compute the motion of characters. So it's a very long love story with computer graphics, and I think most of you are aware of the seminal and very inspiring work of Craig Reynolds that introduced the boids simulation technique at SIGGRAPH in '86. Boids is interesting because it's actually a microscopic simulation, agent-based, and it follows this idea that the crowd motion emerges from local interactions. So in the boids technique, there are 3 rules that govern those local interactions. And there are these 3 displayed on the top. One is that each boids line is motion with its neighbors. It tends to group with other boids, so it is trying to reach the barycenter of the neighbors' positions. And there is also a separation rule to avoid collisions between the boids. So whenever there is too close distance between 2 boids, there is sort of a repulsive forces that push them away. And you can see here the fascinating flocking motion that emerges from this, only these 3 rules apply to each agent. Let me also mention that here you see the original video of the paper that was submitted to SIGGRAPH and that I stole to Dimitri Terzopoulos. He used this video in a course to SIGGRAPH, and it's on YouTube, you can find it. So we contributed to this crowd simulation technique ourselves, and we contributed by introducing this notion of velocity-based crowd simulation algorithm. So let me very briefly explain what it did with. So when we started with this, so it's more than 10 years ago now, force-based simulation technique were really preeminent. So force-based works this way. So an agent is undergoing some forces that will turn into acceleration following the second law of Newton principle. And agents are undergoing or attractive forces, for example, toward their goal, or repulsing forces to avoid collision with other agents. Velocity-based technique work a bit differently, introducing this idea that humans can predict others' goals and motion. And based on a simple prediction mechanism, like by linearly extrapolating trajectories of agents based on their current position and velocity, you can figure out if, for example, there is a risk of collision in the near future. And this prediction is used to define what we call the admissible velocities that are, for example, so depending on the definition you take, all the set of velocities that will lead to a collision-free motion in the near future. So we explored this idea 2007 in a Eurographics paper, and you can see here the video that looks pretty old now. And you can see for each agent the red arrow indicating the desired velocity for those agents, and the blue one, which is the admissible one, closest to the desired one. And as for as for force-based or as for boids, you can explore various ways of defining the admissible velocities. So in this second paper, for example, we defined a set of admissible velocities through a set of linear inequalities based on the relative velocities of agents. And that's interesting because then, okay, these admissible velocities, it takes this definition that you should take a velocity so that you have a collision-free motion in the near future, which means that you keep distance with other in the near future. But if you had a second constraint, which is not to go far away from others, you can also achieve group motion with the same principle. So you can explore many sort of interactions and local interactions of different types by just setting admissible velocities in different ways. And all this reasoning you have in the velocity space to achieve agent motion. You can also explore more complex prediction mechanism. So this linear extrapolation of motion is not right in many cases, simply because, for example, agents, they are constantly adjusting their motion. So their current velocity is not representative of their future motion. So taking this as a prediction is a bit poor. So let me detail this warp driver technique that explore more complex prediction mechanism. Key contribution of warp driver are the following. First, so we have this advanced prediction mechanism based on differences. I'm explaining this through this figure here. So I'm the red, let's say I'm the red agent. I'm wanting to make a right turn into this T junction of corridors. And I'm facing three other agents, the green ones. And you can see a bit of their past motion here. And you can see the environment as well. You can see walls here. So if you try yourself to make this exercise of guessing what is happening next, you can probably figure out that this agent, for example, here on the left, is probably making a turn right, a right turn, sorry, into this corridor. And you can also maybe guess that this other agent performing this weird motion will probably continue making those S-shaped trajectory, but going to the right. And finally, it's not certain what will happen with this agent on the right, if he'll continue straight ahead or turn left maybe. Well, driving is exactly doing this and is computing those probabilities for the future state of agents. So you have this probability in time. So the very near future is red and the further future is blue. And the rate agent is actually considering those probabilities to locally optimize this motion so as to minimize the risk of collision in the future. So the probability of colliding with other agents. So here in this case, it will probably adjust more to the right to avoid a possible collision with this agent. And you update this prediction each time step, right? So it's a continuous process and you constantly locally optimize your motion so as to minimize the risk of collision with others. You can guess that it's quite expensive to compute this and it will not fit crowd simulation. It will not scale to many agents. So actually, this is another contribution of WorldDriver, and also explain the names, that we compute those fields in a very, very efficient way by successive operation of warping. So we start, so I won't go into the detail, would be too complex, but you have to understand that we compute those fields in a very efficient manner. And moreover, since this process of warping, successive warping can be inversed, then you can sample and compute this probability field only where you need that. So only where, for example, the rate agent will try to go. And that's important because then each agent can perform his own prediction of the world depending on the information it has. So you can see examples of results produced by WorldDriver. And you can see, for example, it's successful in predicting the motion of these turning peaks, which is completely not linear, and how it performs better compared to other techniques. You can also see WorldDriver here operating in a constraint example with a complex geometry, simulating the embarking of an airplane. And the prediction of each agent is doing of others' motion is accurate enough so this disembarking look quite realistic compared to other approaches. So in brief, here we can say that a crowd is a sum of individual behaviors, collective behaviors, and local interactions. Microscopic crowd simulation work a bit the same way because you define rules for your agents that are local and they do apply to control their movement. I've shown you the example of the Reynolds boids, where boids, they align, they move together, and they keep separated at the same time. So they apply these three main rules. I rapidly showed you also the Helbing social force model that where agents get attracted to their goal with attractive forces and repulse one another with repulsive forces. And these new rules we introduced with velocity-based techniques that we were far from being alone to explore. And let me mention this. So several groups had the same idea a bit at the same time. And so you can find many variants of velocity-based algorithms in the literature. But the idea is that the agents, they move with admissible velocities and they keep, for example, lower distance bound with neighbor agents in the near future. You can perform group simulation by adding an upper bound to this rule. And Warp Driver is exploring some more complex prediction mechanism and change also the rule by which agents move to make them minimizing locally the probability of a collision. And Scoop, next talk after this keynote will be dedicated to a generic technique to imitate all these previous techniques with a single framework. So please stay tuned after the keynote and check the presentation of OP. Okay, then the question is maybe if this has nothing to do with how humans do, apart the fact that there is a general agreement that humans behave with individually in a crowd, is any of this rule is sort of realistic compared to what humans do? So we asked ourselves this question, and the first thing we considered is this information by which people walk in their environment. And walking is mainly a visual motor task. So vision is the main sensory input when you achieve locomotion. It's a dominant sensory input. Of course, there are other modalities. So human do control their motion from what they see. And you can even try yourself to make this exercise of wondering where you would go in this crowd, right? You can guess a bit because there is this blurring effect. You see a bit of how things move quite quickly, and you can figure out how you would squeeze in this crowd probably. So we design algorithms that imitate this process a bit more accurately. And we've done this by equipping our simulation agents with what we call a synthetic vision system, and equipping them with a sort of retina that you can see displayed here on the right, where we project all the visual information they can access to. And this is very similar to a rendering of the environment from their point of view. There is a lot of deformation here because we give them sort of a wide angle of view. And the most important here is to understand what kind of information we project here. So you see there are two kinds. So the first one is dealing with the bearing angle. The bearing angle is the angle under which you perceive an obstacle when you move. So this is the angle formed by your self-motion and the angle of perception of one given object. And if this bearing angle is constant, you will actually you have actually a clue that you are on a collision course with this obstacle. So let me just take this figure rapidly to describe this. So you are here and you move. So this is agent A moving along this line, perceiving B under a given angle. And you can see that when this angle is constant in time, it's quite obvious that you are heading to a collision. And this is something that, for example, sailors or pilots, they know, because when you have no visual reference on the sea, for example, or in the air, and you are perceiving another boat or another plane always under the same angle, means that you are on a collision course. So you should adjust your velocity. So we do a bit of the same. When one of our agents is perceiving a constant bearing angle with one of those pixels, so white here means constant. It's what we actually project here is the derivative of the bearing angle. So there is a clue of future collision with this pixel, and the agent will perform turning motions so as to sort of give this pixel a turning angle value. And we consider as well the time to closest approach, which is the second information we project here, which tells you about how imminent is this risk of collision. So because maybe you will collide with something, but it's far in time, so you don't care that much right now. So in short, if you perceive a pixel white in those two maps of pixels, in these two matrices of pixels, then it tells that you need to do something. Turn first to avoid the collision and maybe then slow down if it's really imminent. But if you ask agents to move the same according to the same rules, you will have those fascinating emerging patterns from the simulation. And let me say that those patterns, they can be observed in real life. So here the signature of those patterns is sort of strong, but still something you can observe, like the formation of lanes in those bidirectional flows, or the formation of 45-degree lanes in this orthogonal traffic. Something we observe. And what you see as well is we can put obstacle in the scene, and everything is projected the same on the virtual retina. So agents that process the same obstacles, could they be moving or static? Their relative motion is captured by those two variables we compute for it, each pixel. Okay. Same thing that more classical approaches. You can explore various ways of controlling agents. For example, the first synthetic vision was sort of a reactive process. So agents that detect a risk of collision by combining these two information on bearing angle and TTC, and when there's this risk perceived, then they react. So you can do in other ways, such as by exploring this local optimization of a cost function. Let me try to play this video here. So we project a bit different kind of information here, and we combine them a bit differently. So we project directly here the DCA, the distance of future closest approach for each pixel here. Unfortunately, I don't have time to carefully describe those videos, but they are all online. You can check them together with the paper. And we project here the TTCA map. And we combine this information to compute sort of an energy function that tells you about the risk of collision. And instead of reacting, agents will be constantly optimizing the value of this E function by adjusting their velocity. So, and the resulting simulation is, of course, a bit different from the previous one. So, and particularly, this technique is more robust to the changes in density. So, because agents are performing those local optimization, even when the density is increasing, they are still able to find velocity adjustment to avoid collisions, whereas the previous one, agents will be reacting so much that at some point they can get blocked, for example. Then you also mentioned that this vision-based technique, we focus more on how do people extract the information of risk of future collision and how they anticipate this by adjusting their velocity. So it's performing well in a certain level of density, which is quite low or medium, and not meant to perform well in dense situations. So in brief, agents, we could steer them based on this idea of synthetic visual systems, and we were quite happy with that. And same thing, you can explore variants of this idea in the way you define the rules to control agents' motion. And actually, this principle of a virtual retina onto we project this visual information to perform navigation is an interesting way of selecting and combining interactions. So, because agents will react only to what they are capable of seeing of their environment. So naturally, you filter out whatever is invisible or whatever is not perceptible for some reason. For example, it's too far, or it's hidden by another obstacle or something. Something we could also say about this is it's not exactly visual information we are providing to the agents. It's more like geometrical information. So those DCA, TCA values, they are sort of computed from the simulation and directly projected to the virtual retina. So Another question we explored was to figure out if we can use instead more low-level visual information directly to steer agents. And as we know that, so if you check the cognitive science literature, you will quickly find out that locomotion control, one important feature that is provided by the visual system is the optical flow. So it looks like humans are perceiving this optical flow and controlling their motion from this. So we explored this idea of computing optical flows for agents and trying to steer them only based on this information. So the key idea is the following. First, formal relations between self-motion of agents and visual features. I will make this more clear afterwards. So you set those mathematical relations between those two objects, and then you define a locomotion task as a visual task. So I will take example of this as well. Sort of low-level, very basic task. And then you can define more high-level navigation task based on a combination of locomotion tasks. So, and this is done beforehand. And at runtime, then, for each agent, you compute the optical flow perceived by the agent. You extract some features of this optical flow, as well as from RGB images of the environment they can have. And you adjust the motion to achieve the visual task you have defined. An example, the simplest one is goal reaching. So if we ask an agent to reach this purple area here, what we can extract is a barycenter of this purple area from the image. And we do this, we do this extraction. And the visual task for reaching the goal will be to get this barycenter in the middle of the virtual retina. And we have the mathematical relations between the place of objects in an image and the motion. And the agent knows that he has to turn to control the position of this barycenter. We can do goal reaching by just turning so as to take this barycenter in the middle of the screen. Of course, this kind of ideas are directly based on ideas in robotics, where visual servoing is already something concrete and existing. So we got inspired from that, and it's even a collaboration with a roboticist to achieve this. Collision avoidance is a bit more tricky. So let's consider that an agent is moving. Let me take back my laser pointer, sorry. Yeah, so if you consider that agent is heading towards this object, the resulting optical flow will be this one. So it will be sort of expanding, the object will be expanding in all directions. And so the focus of expansion of the optical flow generating by this object will be somewhere here in the middle of the object. And if you have this, that the FOE, the focus of expansion of an object, is superimposed with this shape, means that since it's expanding in all directions, means that you will be colliding with it. So the visual task will be then to separate the shape and the focus of expansion. And again, we have the mathematical relationships between motion and those features, so as to know exactly how agent can adjust its velocity to do this. And this is an example of the motion we get from this rule. Another rule, so you can see that the avoidance of those objects is quite anticipated. So optical flow is providing this, it's called a proactive variable, since it tells something about the future state of objects. You can also achieve following task. by canceling the optical flow generating by a given object here. So if you cancel the optical flow of a given object generated by a given object, means that you are at the same relative position of it. So you typically you are following it. So you can combine those visual tasks and achieve those kind of simulations. So you can see for those three examples here, what is the perceived optical flow, what is the resulting motion seen from the top, and as well as the RGB image of what is perceived for easing the understanding of the scene. So you can see that so our technique is capable of dealing with collision avoidance and goal reaching. So this is this sort of high-level task. It can deal with complex geometries of the environments. Here, as you can see, this is really the input to control the agent. So we keep all the complexity of the scene here to show the robustness of the control. Or you can see that agents, they can react to different kind of moving obstacles, big ones, small ones, moving faster or slower. And one question I had is, what if we switch off the light here? I mean, if in this scene you remove you remove the lighting conditions, the agents should stop because they don't access anymore to any kind of visual information. It's not actually the case here because we're using what we call a synthetic optical flow, which means that to have an accurate estimation of the optical flow, we are projecting the relative motion of things that we know from the simulation directly onto the retina. So this is how we compute. There are other ways of doing this. What you can do is typically compute a numerical optical flow that is obtained from two successive images acquired by the agent. So you can see here two successive images. So the agent is moving, so there is a slight change in the position of things. And using a state-of-the-art technique, you can make an estimation of the optical flow resulting from the relative motion of objects. You can see that it's there is much more noise here, and it will challenge the control we make of our agents. So you can see here a comparison between using a synthetic optical flow on the top and using a numerical optical flow on the bottom, and the difference it makes in the input, and the difference it makes also in the trajectories if you apply the same control rules. The motion of agents will be a bit more jerky because they access to the information later on due to the noise. So they detect the risk of collision with other agents later on. But interestingly, you can achieve a couple of things. So for example, if we ask an agent to move in this dark street, you see that there are dark areas where you don't have this public lighting. And if you look at the generated optical flow, you can see there is an absence of flow here. And we don't know if this absence of flow is due to the absence of motion in the image or to the absence of light in the image. So we need to figure out. So it means that we also need to process the RGB image of perceived by agents and detect. So we segment dark areas. So we know by combining these two information that there is nothing moving here, so it can be safe. But since it's dark, there is uncertainty here. So we prefer not the agents to go there. So if you check his trajectory here, it will be actually avoiding those dark areas. I forgot to mention that optical flow is the apparent motion of pixels in a given image. I hope that this is something that was clear to you. Otherwise, the three last slides maybe was a bit painful. So anyway, in this talk, that I entitled from kilometers to millimeters. The idea was the following one. So actually trying to generate animation systems to populate very large environment, reaching the size of cities sometimes. We have finally got progressively interested into understanding how do people actually control their locomotion. So trying to achieve more and more realistic crowd simulation, we finally ended up by exploring what was happening with the visual system of humans and what was projected on the retina and how they were extracting this visual information that let them safely perform locomotion in the environment. So from this, I would like to conclude my talk by opening few perspectives of this work. First is, since we are able to create those populated environments with crowds, etc., we are also able to immerse them into using VR technologies into those crowded environments. And it has a lot of value because we can take advantage of this to easily control the environment, repeat the same conditions over several people and have easy access to behavioral data. So understand even better how do humans perform collective behaviors, how they control their motion there, etc. This is what we did by also exploring the gaze activity. And what we first did is figure out if people have sort of the same behavior in VR and in reality. So those two videos are synchronized and normally meant to loop. Let's try to launch them. Okay. You can see the efforts we have made to reproduce real environments, reproduce not only the aspect, the geometries of buildings, the aspect of buildings, but also the kind of people moving there, densities and position of people there. And we compare both how people were moving and what they were looking at in such environments. And this is important because after having checked that behaviors were similar, we can perform studies where we check what people look at when they move, because we have proven as well that there is a link, for example, between people you gaze at and people you avoid. So you tend to gaze people you avoid. So it means that you are capable of detecting those characters with provoking a high risk of collision with you. And it tells a lot about what is the kind of information you take from the environment and what is the kind of interaction neighborhood you are considering. So it's really giving insights for modeling crowd behavior there. Another perspective is data-driven crowd simulation. Ming-Lin talked about this in her keynote last Monday, and we share this idea that data-driven crowd simulation are probably better than handcrafted crowd simulation models, typically the one I went through up to now, and because it can capture everything that is not captured by an handcrafted model, and it can go beyond walking behaviors only. So we are exploring this ourselves as well, especially in a robotics project where robots use this kind of technique to predict what will happen next around them, especially the trajectory of people around them, and to perform safe navigation in such environment. More generally, we believe that there is an interest into having this loop that real data, they can tell a lot about how people behave, and we can learn from that and generate synthetic environments that resemble those real environments. You can immerse people into those environments. Just as I showed before, you can generate synthetic data out of those simulations that you can use then to train those data-driven crowd simulation or evaluate them, and you can analyze better or predict better real environment, so you can capture better real data and then have this improvement, cyclic improvement, this circle of virtue principle in our research that we apply. So let me take an example of the kind of immersive environments that we create here, and what the kind of task we ask users to perform, such as traversing a crowd. And you can imagine what it would take, what it would ask to have the same data only based on real experiments. You will have to gather all these users here, and we've done this in the past, and it's really, believe me, it's really painful. So here you can generate a lot of interesting data, such as here, how do people squeeze through this kind of very crowded environment, how they can use, for example, shoulder motion to squeeze between people. Actually, what we were exploring in this experiment more precisely is the need for haptic rendering in those virtual crowds, the need to render contacts you make with the environment to further improve behavior of people, of users in the environment. Last perspective I would give is about the need for simulating and predicting better large scale and dense crowds, and in particular to deal with this kind of phenomenon where you have a transition between social interactions to physical interactions, and when interactions turn into physical, simply said, when people start pushing one another, so you are entering a sort of danger zone here. And it's really important that crowd simulation tackles those kind of questions. An example we are working on right now, sorry, I'm spoiling a bit some unpublished work, but we are considering this kind of motion. So if you look carefully at my video, I hope you can see it good enough. You will see that there is a shock wave here, a density wave, traversing actually this audience from the back to the stage here. And people are simply lifted in the air, transported by some meters, and then dropped by the crowd, and it's a really dangerous phenomenon. You can see it from the stage. You can see people really pushed front. You may recognize also the band that is playing here. So you can find this video quite easily on YouTube, looking for the Manchester Oasis concert 2005. And we are in the process of devising simulation models that can reproduce those kind of phenomenon. And hopefully, so we will let you know more about this quite soon. So this ends my talk. I'm just displaying the list of papers, and I mentioned more carefully here in this presentation, so that if you are interested, you can go back to the details here. And to finish, I would like to thank my sponsors. Funding this research is of course very important. So especially European and national fundings that we were given. Many of the work I talked about were collaborative ones, so I would like to thank my colleagues and all these people that participated to this research. And more importantly, I would like to thank all the students, postdocs, PhDs and engineers working on this work. They are really the ones making this possible. So we look a bit different right now. So if we are to meet soon, so we look a bit more like this right now. So we really hope that real crowds will be back, because this is our topic of research. So we need them. And to finish, I would like to thank the audience for listening to me today. Thank you very much.
All right. Thank you, Julien. That was a great keynote about crowds. Yeah, as you said, is a hot topic, right? Because it's related to what's going on these days with the pandemic situation that we're living. Okay, so we gathered a few questions from the audience. I also have some questions myself about the great content you talked about. Simon Feneley in the Discord ask if the agents are using geometric information for their vision, they probably don't get you probably don't get agents that are being confused by the visual illusion. So they don't really so agents don't get confused by what they see, no? For example, he's wondering about they don't take into account signs, like when they walk, if they find a exit sign or a direction sign or a this way sign. This doesn't, agents do not take it into account. No? So I think as a summary, maybe the question here is like, how do we take the semantics that we see around us also into account, right? Because you talk about this visual flow and then flow gives you some sort of geometric information, but then what about the other information that as a humans we see around us? Do you take this into account?
So to be clear, no, not in the kind of technique I've shown, but we are working on this as well. So we have a recent paper dealing with this question by my postdoc Wouter van Tol. So I'm happy to share the reference of this. But let me answer more precisely the question. So what we extract so far is a really low-level visual information to achieve basic locomotion tasks. So what I call actually high-level navigation tasks are not that much high-level. It's very common that in some in a crowd simulator you have different levels of sync. So you have the very basic, which is how you perform the walking motion in controlling the joints of characters. I didn't talk about this. There is this level where you deal with local interactions with people, with the environment at low levels. This was the focus of this talk. And then higher level, you can have path planners or dealing with this higher level information that you could extract actually from image analysis, something that is doable, but we did not perform. But Wouter recently introduced this idea of having a strategic level where you can define a couple of things, including how agents should react to signs. So yeah, this is something doable. This is something we've done in some work. Nothing I talked about today.
All right. Okay, that's good. That there's always more stuff to do, right?
Absolutely.
So Sheldon Andrews, also in Discord, he asked, he says, a lot of the crowd simulation methods generate smooth trajectories for characters. And then he wonders if there are techniques that generate more non-smooth and discontinuous paths that we might observe doing, for example, when we want to avoid obstacles or stuff like that. Is that, if this smoothness of the path is something that we generally see in the crowd simulations? Do you handle non-smoothing particularly, or can you comment a little bit on that?
Yeah, we tend to prefer a smooth simulation. The reason is simple: is then you connect to an animation system to have those characters moving. And when you deal with non-smooth trajectories, you need to have this character animation system that will compute the walking motion that are capable of dealing with non-smooth trajectories. Okay, so it can be a difficulty for us. I mean, there is still a need and we see lots of ongoing work that could probably answer all those needs, but we really need those techniques for animating characters that can handle non-smooth trajectories. What in the question of do we generate non-smooth trajectories? The answer is yes. If you check what I explained with synthetic and numerical optical flow, so if you degrade the information from which agents move, then you tend to have those more jerky trajectories. And that's interesting because actually, indeed, when we have strong reaction, when we have strong adjustment of our velocity, probably because there is something sudden that appears in our environment, or we perceived quite late. So we have a very short time to react, and you have this strong reaction. So yes, by limiting the information accessible to agents to control their locomotion, yeah, you will probably get non-smooth trajectories.
Mm-hmm. Interesting. Some other questions. This one is from Tomer Weiss, also on Discord. He says, have you considered biomechanical agent limitations for the velocity base or other collisions avoidance methods? For example, the movement's capabilities might be constrained in different ways for agents that are jogging versus walking, or for disabled agents. So,
yeah, not easy to answer this one. So actually, the agents, as you can see, very often represented with those moving circles, are very, I mean, it's very basic. It's far from capturing the biomechanics of walking people. There are some techniques that, for example, simulate how people perform steps that can probably deal better with this kind of limitation. And also, for example, talking about smooth trajectories, as you can see in the trajectories we generate, you don't have this lack of swaying motion. So if you track real people in their environment and you look at their trajectories, first thing you see is it's moving with this swaying motion, very, very visible, and you filter this out so that you fit better to your model of humans. Something that data-driven crowd simulation could really well answer, on my opinion. So social ways is a technique based on GAN to generate human trajectories based on existing data sets. So whatever this GAN generates in terms of trajectories is something that humans can do. So implicitly considering the biomechanical constraints.
Mm-hmm. Oh, yeah,
there are many ways
yeah. I mean, it's the fact that the agents are represented in a very simple way, right? So we need to enhance these agents in order to enhance the overall simulation. Okay,
it's true that improving the modeling, the biomechanical modeling of humans is one way. And some of the groups really follow this direction. What we explored was more accurately capturing the input of the system more than the output. Let's say the mechanical output, so the motor.
Yeah. Okay. There's more questions, but I also have a question I wanted to ask. So of course the question is about the current situation that we're living, right? So we are living in this pandemic situation where in most of the countries, crowds are forbidden, but not even crowds, like even groups of 10 people, right? So then I wonder if the knowledge that we have now in crowd simulation can directly help in the context that we have right now in the world, or there is research to do such that we can find, methods that help in handling the current situation. Is there something specific that needs to be investigated, or do you know a particular technique that you would use directly to simulate environments in the current context?
Yeah, so I think crowd simulation can be helpful in two ways. First of all, crowd simulation generally benefit to crowd safety issues. So, like managing operational management of crowded environments. So, it's quite obvious that you can predict better how traffic will go in a given environment, and you can arrange this environment to diminish, for example, the proximity between people. So this is quite obvious. But another way is understanding the dynamics of a pandemics. So there are a category of model devised by epidemiologists, which are called the SIRS model, SIRS model, right? And they combine a motion model where you can see agents. So it's simplistic environments, right? Very simplistic. But you can, for example, simulate a bit how is a proximity between people having a urban life or in a given working environment. So you can tell a bit about the statistics of people, how many people they meet in a day, what is the proximity with those people, using basic motion model here, combined together with a propagation, how to say, the way a virus can contaminate people. So you have this contamination model on one hand, you have this motion model on the other hand, and you can combine the two to sort of model the dynamics of a pandemic. That's very interesting. But I think crowd simulation can provide tools to perform a more accurate, more precise estimation of those statistics. How long you stay close to people, how close you are to people, how frequent you meet new people, and understand and come with a more accurate estimation of proximity statistics that could be useful to understand why, for example, in a restaurant, in a bar, you have more, apparently, more propagation of the virus than in other places like a working environment also.
Mm-hmm. Did you guys get approached, but any, I don't know,
we have
entity
made,
that wants to...
we have made contact with the Institut Pasteur in France, but I think there is, so there was fast reactions from our institute to try to help with this, but I think here we probably need a bit more of fundamental research. For example, to make direct relations between motion, proximity statistics and how virus propagates. So it's a more long term. So we have entered into a discussion, but I think we are heading to a more long term research here.
Mm-hmm. Okay, that was great. Okay, so I think that we can wrap up the session here. I mean, we finished with this open question of our current situation that crowd simulation can directly help. So I think it's a nice way to finish the conversation. So I want to thank Julien once more. I mean,
thank you very much again for the invitation. Thank you. We had
a great talk and a great round of questions. So so we're gonna finish the session here. Just to stay tuned. In roughly 5 minutes, we're gonna start the next technical paper session, which is actually about crowds, and there's a paper actually authored by Julien on that session. So make sure you don't miss it. See you in a few minutes. All right, welcome back to I3D 2020. We're back live and we're ready for the paper session 6, which is about characters and crowds. So if you like crowds, we have 2 papers on crowds and another one on character animation. So in this session, we're going to have 3 papers. It's going to be presented by Wojtek Bangtol, Tarindu Matthew, and Tianqing Li. Which are here in the room talk, in the Zoom talk, ready for the Q&A. So we're gonna now watch the 3 papers presentation, and we'll see you after the presentations for a Q&A. Make sure you post questions on the Discord channel on the YouTube. Well, see you later.
Hello everyone, my name is Wouter. I am a postdoctoral researcher at Inria in France, and I will be presenting a paper that we wrote with our research group titled Generalized Microscopic Crowd Simulation Using Costs in Velocity Space. I will start by giving a quick introduction to the topic, which will also motivate our work. In general, crowd simulation means using computer models to simulate the motion of human crowds, preferably large crowds with many humans, and preferably in real time, so that it can be used for applications like gaming or interactive applications. There is a big category of crowd simulation approaches that are called agent-based, and here the idea is that you simulate each person as an individual intelligent agent with its own properties, its own goals, and also its own algorithms for achieving those goals. There's a distinction between global path planning, where an agent just plans a path to the goal, and local navigation, where an agent tries to follow this path during the simulation while avoiding collisions with other agents, for example. Now, this paper is purely about the local navigation component, so that's good to keep in mind throughout the presentation. Local navigation is something that every agent keeps doing in every frame or every step of the simulation loop. So at any moment in time, the task of local navigation is to update the velocity of an agent in such a way that it fulfills certain wishes. For example, an agent will want to more or less move towards its goal, but it will also want to avoid collisions with other agents that are walking around. But you can think of other demands, other aspects, such as agents that would like to stay together in a group and so on. But the most important component of this is moving towards the goal and avoiding collisions. And this is collectively referred to as collision avoidance, or sometimes as microscopic crowd simulation. If you do a quick Google Scholar search on collision avoidance, you will see that there's a lot of research on this topic. There are lots of papers presenting different collision avoidance algorithms, and naturally there are also many different implementations out there. And all these implementations are a little bit different, they have slightly different details, or the algorithms are based on different principles. So this makes it very hard to do any kind of comparison or to make any statements about which kinds of algorithm works best for which scenario. This is why we saw the need for a general framework that describes all these algorithms via one principle, and then an implementation that implements these algorithms. And that is exactly what this paper is about. So in this work, we show how many collision avoidance algorithms can be translated to one shared principle. And I will describe this principle in more detail later. And next we present an implementation that is open source, so everyone can use it freely. And this implementation includes many state-of-the-art collision avoidance algorithms. And we hope that it can serve as a platform for honest comparative studies between algorithms. And finally, we demonstrate this software by showing 8 different algorithms side by side in a number of scenarios. Okay, now that we have this overview, we can zoom in more on the local navigation framework itself. Local navigation is part of the simulation loop, as I explained earlier, and in every iteration of the simulation loop, we do a certain sequence of steps. The first step is to create a spatial hash, a data structure that agents can use for finding their neighboring agents. A typical spatial hash is a KD tree. Then the next step is to let each agent use this data structure to find nearby agents. So for the dark agent in the middle that we will focus on, the query could look like this: find all neighboring agents inside a circle. Then the next step is to compute a preferred velocity for each agent. And this is usually the input of a collision avoidance algorithm. And that is why it's required here. And the easiest option is to just take the vector that sends an agent towards its goal at a preferred speed. Then the next step is local navigation, which is the main thing that we will focus on. And this can be any routine that uses all the information so far, so the preferred velocity and the neighboring agents, to compute an acceleration vector that tells the agent how its velocity should change in the upcoming step. Then there is a concept called contact forces, meaning that if certain agents are already colliding, you will want to apply a certain force to push them apart. Usually you will want to avoid collisions altogether, but sometimes you cannot avoid it, and then contact forces can be useful. And finally, with the forces and the acceleration, you can update the agent's velocity and position via, for example, Euler integration. And at the end, when you have done this for all agents, every agent in the crowd will have advanced by a certain step, like this. So as I said, we will focus on the local navigation step of this loop. As I said earlier, there are many different algorithms for local navigation, but overall they can be categorized as follows. There's one category of algorithms that is based on forces, where you model an agent as a particle that is pushed or pulled around by certain forces. Another category is called velocity-based, where an agent actively looks for a certain velocity to use. So this is more active, whereas the force-based approach is more passive. And finally, there's a category that you could call vision-based, where you try to approximate what an agent actually sees via rendering techniques, for example, and then use this information to update the agent's velocity. But in this paper, we show that all these different principles can be generalized as follows. You can say that a local navigation algorithm is a combination of a cost function and an optimization method. What does this mean? Well, let's take another agent as an example that is moving at a certain velocity. We could define the velocity space as the set of all velocities that this agent can currently use. If the agent has a certain maximum speed that it can attain, then this velocity space can be visualized as a disk, where the boundary indicates the maximum speed, and the x and y axes indicate the x and y components of the velocity vector. And of course, the velocity that the agent is currently using lies inside this disk as well. Next up, a cost function is a function that assigns a scalar cost to any velocity inside this circle, where a lower cost means that the velocity is more attractive to use. For example, attractive velocities would be those that take the agent to the goal without causing collisions. So this gives us a scalar field which assigns a cost to any velocity inside this disk. So you will have a disk-shaped area with low cost and high cost parts. Finally, an optimization method is a way to use all this information to update the agent's velocity. Roughly, there are two things you can do. You can look at the gradient of the cost function at the agent's current velocity and then move away from this gradient so that you sort of greedily go to a velocity with a lower cost. And the other main option is to look for the best velocity in the whole space and then move towards that. And usually this is done via sampling, so by just trying out a lot of velocities in this space and then picking the best one. But there are also algorithms that don't use sampling, but they compute the optimal velocity in an exact way. The paper proceeds by showing that force-based, velocity-based, and vision-based methods can all be translated to this principle of a cost function plus an optimization method. For this presentation, I've chosen to leave out the details because they are very technical, and it's more interesting to look at some results next. But the takeaway message here is that the translation is indeed possible for all these categories of algorithms. Having said that, I will now move on to describing our implementation and showing it in action very quickly. Our implementation is called HUMANS, which is short for Unified Microscopic Agent Navigation Simulator. It's written in C++ and it implements many state-of-the-art collision avoidance algorithms. And these algorithms are detached from the rest of the simulation as much as possible. So details like KD trees and nearest neighbor queries and time integration, they are not part of collision avoidance and they are nicely detached. So researchers can really focus on what the differences are between collision avoidance algorithms. The code is open source. It's available freely for everyone on the Git server of Inria, our research institute. And for now, our main target audience is researchers, so people who are interested in understanding collision avoidance algorithms in more detail. So in humans, it's relatively easy to take any cost function and any optimization method, combine them and see what happens. And if you know a bit of C++, you can also quite easily write a new cost function yourself. And with that, we hope that humans can become the new standard platform for research and experimentation with crowd simulation. This is a fragment of the supplementary video for this paper. It's just a proof of concept to show that one implementation, one principle can indeed replicate many different collision avoidance algorithms. So we show 8 different state-of-the-art collision avoidance methods side by side. Okay, so let's finish the presentation with some closing comments. To summarize, collision avoidance is a key component of crowd simulation. It has received a lot of research attention, and because of this there are many different collision avoidance algorithms and implementations. And this is why we have translated all these algorithms to a single principle, namely cost functions in velocity space, and we have presented an open source implementation of this principle, which can then hopefully serve as the basis of future research on this topic. Humans enables honest comparisons between collision avoidance methods, and it simplifies the creation of new ones. Of course, we have only looked at collision avoidance, but it would be interesting to see if the same concept of cost function optimization also applies to path following or maybe even path planning, and this would be a big contribution to crowd simulation research in general. It would also be interesting to look at other optimization methods. So for now we have looked at sampling, where you try out lots of candidate velocities and then choose the best one. But this is computationally quite heavy because you have to evaluate the cost of a lot of candidates. But you can imagine that something like gradient descent is a more efficient procedure that might give you a velocity that is almost equally good or maybe even the same. So this is an important thing to consider in terms of performance. Now, the most logical next step is of course to do a real comparative study between collision avoidance algorithms. But for this you need to think carefully about which scenarios you want to try out and also how you want to measure the quality of a simulation. So there are actually lots of related open questions that are really interesting as a future research topic, I think. Okay, that's it. Thanks a lot for your attention. If you have any questions about this work or about crowd simulation in general, you can always send me an email. My email address is displayed here. Thanks again.
Hi, my name is Tarinder Matthew, and I'm going to present our work on inverse spatiotemporal crowd motion design. Crowd motion can get pretty complex. In this scene, we can see hundreds of people moving in at least 8 different directions at a given time. So our question comes as to how we can easily represent and author something like this. Even though these complex scenarios can be scripted, that can be very time consuming and hard to create and can become tedious very fast. So we want to create this type of scenarios fast, like maybe in less than 1 minute, and try to identify these patterns and formations that we see that the people go through and come up with a scheme of copy pasting styles over so that we can create these sort of complex scenarios. I will first now take you through some related work, then discuss the method and show you some results and conclude with some future work. Crowd sculpting is a 2014 work where they encode repetitive crowd motion and encode it in a graph structure in a way that it can be interactively stretched, and this repetitive crowd motion can be stretched across space and it stretches across time as well. Cloning crowd motion is another work from 2012 where they collect a set of real trajectories, making use of lab conditions where people move around, and then create patches of these trajectories and then use an optimization to blend these together to create larger and larger scenarios, allowing you to extend this repetitive motion through space and time. In this work, they present an interactive cage-based manipulation method of existing trajectories so that you can create a new pathway and add some sort of collision-free trajectories in creating new scenarios. Contrasting to previous work, our method focuses on blending in synthetic and real trajectories together and creating new scenes by blending in styles, creating completely different motions in different environments. Our sketch tools allow to draw people, a source and a path, and geometry. The input of the sketching tool gets converted to a set of trajectories by making use of a crowd simulation engine. The synthetic sketch will get converted into a set of trajectories similar to having a real dataset. Real data from datasets such as the pedestrian dynamics data archive also is accepted as input to our system. Now we focus on the inference phase. In the crowd motion model, we assume that each crowd has a source, destination, and a path. In the initial step, we apply a density-based spectral clustering at t equals 1 and t equals capital T, which denotes the final time step. This identifies the source and destination of each crowd. For path segmentation, we make use of the segmented linear least squares algorithm. Since it works for a monotonically increasing ordered set of points, this works for our problem. We extend the original solution, which makes use of 2D linear regression to 3D by making use of PCA and solving for the largest eigenvector. In these examples, we show the algorithm applied to a crowd moving in a sine wave form, the sine wave form with a lot of noise added, and a stop-and-go motion of a crowd. Here we illustrate the motion of the crowds. For each linear segment, we store the angle and speed of each trajectory of each virtual human. Thereby, we are able to produce the exact motion of the crowd or able to process it and resample it. Now let's move on to the design phase. Through an optimization process, we iteratively move the source and the destinations when it's moved to a new location. And we also warp the original path towards the shortest path until all elements, including the source and the destination, doesn't overlap an obstacle. We can retarget paths using a change of the path itself or the change of the order. In this example A, a spiral-like path is resampled along a U-like path to create a spiral motion along a U path. In C, you see a stop-and-go motion resampled and creating different stop-and-go motions as shown in example D. Now let us look at some interesting results. Here we retarget this with a stop-and-go motion from the PDDA database. Here we retarget it with a synthetic spiral motion. Here we retarget it with a new grouping. Here we create a crowded market. Now we create an artistic squiggly motion and retarget one of the crowd groups with this squiggly motion. In this example, we create a four-way crossing, making use of sketch tools and some copy pasting. We then make use of temporal keyframes to create a second iteration so that we can create the final four-way crossing. Now we remap it to a three-way crossing, make use of our source destination retargeting. In future work, we hope to introduce dynamic grouping of crowds, such as leader-follower formations and more social group formations, automatically recognizing these sort of aspects of crowd motion. And we also would like to introduce a sketch-based language for crowd motion authoring, making it even easier to author complex crowd motions by creating sketches on a digital canvas or something like a whiteboard. Finally, we'd like to acknowledge the following grants for supporting us in this research. Thank you.
Hello everyone, my name is Tianxin Li. Today I'm going to present our work entitled As Dense GATs, a graph attention-based network for nonlinear character deformation. In animation production, it is great important for animators to achieve the high quality of character deformation with complicated appearance. In this work, our motivation is to explore a deformation method to automatically compute deformations for new characters, thereby decreasing the time spent manual work. Most related work for deforming characters could be roughly classified into following groups. For geometry-based deformation, two well-known methods, LBS and DQS, are widely adopted in real-time applications due to the computational efficiency. However, they also suffer from the undesirable volume loss and joint budging artifacts. These artifacts need to be further manually fixed by highly skilled animators. This time-consuming process had to be repeated while deforming new characters. In contrast, physics-based method can achieve the convincing deformation effects by formulating the deformation process within a simulation framework. On the other hand, once the deformation parameters are specified, it is difficult to control the resulting shape of character in each animation frame. Furthermore, the physics-based deformation is computationally expensive and usually avoided in interactive applications. Learning-based deformation method try to learn the surface deformation as a function of designed parameters. For example, SMPL model can represent a wide range of human body shapes in varying poses. The parameters of the model are learned from the existing data, and the model could only be used for predicting the human body with fixed number of vertices. In the work of FDDA, they used feed-forward networks to approximate nonlinear deformations to achieve high accuracy while enabling real-time animation. However, once the networks are trained, they could only work for one specific character, and the application to new character is limited. Recently, neuroskinning addressed the model generalization problem by training a graph neural network. The trained network could predict skinning widths for production characters with varying number of vertices and bones. In this work, to address the above-mentioned problems, we propose a graph learning-based method to end-to-end predict offset adjustment of each vertex for nonlinear effects. Our proposed deformation method provides two key contributions. First, we explore an integrated deformation system which can directly result in complicated deformations for new animated characters by learning from the available artist-designed skinning features. It could greatly decrease the repeated manual work. However, learning such a huge amount of complicated features is not an easy task. Therefore, we additionally present a novel densely connected graph attention-based network named dense GATs to achieve the goal of automatically generating nonlinear deformations. We adopt the idea of regarding deformations as a combination of linear and nonlinear parts. The mesh of the animated character is firstly roughly deformed by the linear-based method. The resulting deformations have visible errors, and we then use the network to produce the nonlinear corrections. These linear deformed meshes are parameterized with the graphs, which are then input into the network. We use various characters with different customizations in random poses for training and make the network possible for building the intricate relations. The trained networks directly output the corrective displacement of per vertex for the final nonlinear deformations. We use the formulation to conclude our pipeline. So given a character in rest pose, through the transformation S of each bone in the skeleton, we first use the linear-based method to deform the mesh. In this process, because skinning weights are directly computed without manual modification, the deformation result TS is inaccurate and visibly different from the target deformation. To correct this difference, we further refine the linear-based deformation TS based on its mesh graph G and generate the remaining nonlinear correction HG. The final deformation could be expressed as TS plus HG. We next introduce how to construct the mesh graph G. We expect the input of our network to be the graph G, which stores features of vertices and edges. Here, V denotes the set of vertices, and E represents the edges. The adjacency matrix U indicates whether there is an edge between pairs of nodes. We next assign attributes to graph nodes. For one node, its attribute vector can be defined as Vi with 3 elements. Pi is the vertex position, Ni is the normal of vertex, and Si is the distance vector to all skeleton joints. In this way, Vi contains both mesh geometry information corresponding mesh vertex and the relative position to the skeleton. In total, the dimension of Vi is 6 plus the number of joints J. Then, the features of each node are transformed through a nonlinear feature transformation module. The module consists of linear layers followed by nonlinear activation and normalization. By this features mapping process, the features are transformed into normalized high-dimensional features that could provide rotation and translation invariance in some degree with enough training data. Next, we input the obtained features to the network to approximate the corresponding correction. There are some challenges for training models to realize this approximation. First, the mesh geometry is arbitrary and its features are complicated, so how to deal with this data and how to map it to the nonlinear offsets. Second, for the huge number of features, how to make the training easy to converge. Then, if we use a deep network, how to resolve the gradient vanishing problem. Regarding the challenges above, our proposed network dense GATs has 2 main technical contributions: GAT blocks and their dense connection pattern. Let's first take a look at the GAT block architecture. To deal with arbitrarily structured mesh graph data, our method uses GAT blocks for effectively learning mesh features. Specifically, it consists of two streams. The graph attention-based aggregation stream is used for computing the hidden representation of each node by aggregating neighboring features with different weights. In addition to this, we also introduced the self-reinforced stream for increasing feature multiscale expression that linearly maps the individual features of each node. In this way, the GAT block can effectively compile information on complex graph features from neighboring vertices as well as information on self-features. We use FGATB to represent the process through one GAT block. Due to the complexity and the large amount of features in our mesh graph, we need to apply very deep networks to benefit from their advantages. However, for training deep graph convolutional networks, the problem of gradient vanishing will become more serious as the number of network layers increases. To address this problem, inspired by DenseNet, which is used in CNN, we introduce dense connection pattern to densely connect our GAT blocks for further training deep layers. If the layer of the first GAT block is L, after M GAT blocks, the result is fusing all the intermediate layers' outputs. We refer this architecture as dense module. And this is the overall structure of our dense GATs. There are 3 dense modules, in which comprises 6 densely connected GAT blocks. Between 2 adjacent dense modules, we adopt one GAT block as the transition. This operation plays the role of information integration. To evaluate our proposed method, we train the network with 125 characters with different customization and animate each of them with 8,500 poses. Then, we test the trained network by using 20 characters with random motion sequence. We first show the result of the correction from linear-based rough deformation to nonlinear one. The test character is animated with dancing motion. It could be easily seen that the areas with large errors can be well corrected, and the result deformation become more plausible and realism. We also provide an intuitive demonstration of the prediction error compared with the ground truth. As expected, the network is able to generate visually plausible deformations without noticeable artifacts. The trained network can also improve the detail deformation. We take the characters with Kung Fu motion as an example. The approximated results by our network can correct the artifacts of volume loss in the region of elbow. This correction is end-to-end predicted by our network without need of traditional manual weight modification. We also provide a comparison with other 4 different network architectures. We evaluate the prediction distance errors. The first is the result approximated by our dense GATs that almost deformation could be well predicted. Then, we evaluate the architecture of the original GAT, the neural skinny network, and our dense GATs without a self-reinforced stream and without the dense connection pattern. In contrast, with our proposed network, the best prediction result can be obtained thanks to the operations of self-reinforcement and dense propagation. For such an example character, the timing for approximation with our method is about 31 milliseconds per frame. To conclude our work, we have presented a dense GATs network that leverages existing well-designed skinning features of characters to accurately predict deformations for new characters. Our approximation is an end-to-end process that can directly predict each vertex deviation in each animation frame. Our GAT blocks and dense modules allow for efficient utilization and transmission of self and adjacent information through the network. There are also a few limitations and potential improvements that could be addressed as future work. First, the network generalization ability is substantially dependent on the character mesh information. In the future, we would like to design more effective feature representation method to express the graph information. Second, our approximation mechanism cannot be applied to dynamic behavior simulation. Finally, we train all characters together and do not consider the material attributes of different garments or skin. To perform perfect visual effects of deformations, future work can independently train networks with different materials. Thank you for your attention.
All right, welcome back. So we just watched 3 great presentations about crowds and characters. So now we're gonna go ahead and have our Q&A session for session 6. I've gathered a few questions. We're gonna go in order, okay? And then if you guys wanna jump in and comment, feel free to do so. So first we saw the paper by Walter, and Thomas Weiss in Discord asks, I understand that velocity cost is different for each method. Did you consider linearly combining with some sort of weights the different results into one cost function for getting a better simulation?
Yes, nice question. It was actually one of the secret extra motivations to encode all these different algorithms with one principle, because before these combinations would be hard to make because every algorithm works a little bit differently. But now with this framework of cost functions, it's indeed pretty easy to combine them. I don't have an example myself where the result is actually better than if you would just pick one algorithm. But at least the basis is there and we can definitely experiment with it.
Mm-hmm. Nice. There's actually a follow-up question. They said, I'm wondering if you can somehow use the insight here to develop a pure data-driven method, since the universal cost function you described can be used to say, for example, using a reinforcement learning or similar method that controls the agents. Have you thought about using this as a cost function to train a method?
Yes, actually somebody in our team is doing something like this, and it's a logical question to ask. So yeah, I think this velocity space it's a useful representation to use as a basis for learning.
Mm-hmm.
And so I haven't worked on this myself, but I know people close to us are doing it, and it seems indeed like you can use reinforcement learning or some other learning method to gradually create so to maybe start as a basis with one cost function that you already have, and then use data to maybe change the shape of this scalar field in the velocity space. So I can imagine that if you give it enough data, it will improve and become maybe closer to what the videos do, what your input data does.
Mm-hmm. Let me see. Okay. Sorry. Okay, so there's another question from Discord, also to Walter. You mentioned velocity attribute for each agent. What happens if an agent is accelerating or decelerating? does the model account for such scenarios for collision avoidance? And in that respect, have you considered a method like Verlet integration for taking such things into account?
So I think in the presentation I said that eventually the method, every navigation method produces an acceleration vector. So we keep track of this acceleration as well. So we don't just use it immediately to update the velocity per agent, but we keep track of both things. So with that, it's possible to do Verlet integration. But I think maybe the question is also more about are there collision avoidance methods that use this concept of acceleration in their prediction step? And if you remember the keynote from Julien, there was a warp driver method that uses that gives more specific predictions of what will happen next based on what has happened in the past. And in that model, it's possible to do something like this. But the 8 methods that are in the video and in the presentation, they are purely based on the current velocity of all neighboring agents. So they purely use the velocity as input. But it's definitely possible to use anything else that you can get from a neighboring agent.
Nice. And then the last question is from Sarindu, here also present in this chat. So he wonders, were there any scenarios where each method would behave wildly different?
There are a few conceptual differences in algorithms. Like some are more careful than others. That you can have the one model lets lots of agents stand still and wait for the problems to resolve, and then it sends these last agents forward. Whereas another model is maybe more selfish, where people just rush straight forward and hope for the best. So you can see these kinds of patterns. So it's mostly these high-level things that you would also expect based on how the model works. We didn't really run into any big surprises yet. That's usually if something happens that we didn't expect, it was due to a bug. So yeah.
Okay, nice. Well, I look forward to follow-up work. That's a great paper. Yeah. Okay, now we jump into the second paper. We have a few questions for Tarindu. I wonder what kind of users did you use your sketching interface, and if it's really proven to be used for anybody, or you need to have some sort of understanding of crowd simulations to use the method.
That's an interesting question because it actually inspired the future work that I talked about, because you needed some understanding of crowd simulation to make use of the interface and to copy all the styles. It wasn't that intuitive enough for, I would say, layman users to use. But this inspired some future work that we are working on related to maybe a more intuitive sketch-based language for authoring.
Yeah, I mean, I wonder, right? Because you said that some future work is like how to model dynamics and how to incorporate more stuff into here. So then there might be a barrier on the kind of, you said, language or capabilities that you have, your sketching capabilities in order to add this, no? So I wonder if you have any insight on how can you make it easier, or for the non-expert users, how can they specify some more complex behaviors?
I think the important aspect here is to try and simplify or be able to abstract out the complex behaviors, because some of the videos that we see that have very interesting crowd motion are actually, you only see those interesting behaviors because they are sped up very fast. And so if not, it doesn't look that intuitive. So this time aspect also comes in as well. So sometimes the source material itself has this interesting motion just because it's been edited to show that behavior. So when you show something interesting like that, I noticed that we noticed that even people who are not trained are able to abstract out this interesting behavior and try to come up with this specific authoring. But I think there's a lot of space to explore, specifically when it comes to like rapid prototyping of crowd authoring, etc. Because there's
yeah. I mean, user interface is already an entire field, right? So one can think about writing the proper user interface for this kind of methods. And actually, that brings me to my next question, which is like how. So when we talk about the scale, like fine scale or coarse scale, how do you incorporate all these subtleties into your sketching approach, right? Because in the end, you want the user to be able to control maybe individuals or like larger scale behaviors, like micro to macro scale. Is this something that you already take into account, or at the moment it's just one level of detail, let's say, and you want to build from that?
Yeah, so we are definitely above the area of where it's focusing on single character animation, but we are more towards the crowd animation where we expect some sort of group behavior. So that's what we focus on. But there is definitely, I guess we chose a level to focus on 10 to 100. And we are very much interested in large-scale behavior because some of our previous work was working on designing large-scale urban spaces for crowds, etc. So we were really focusing on 10, 100,000, that level of scale. So it was mostly
So you have like a one level of detail sort of thing. You don't have like. You cannot control like different levels of detail independently, no? Like it's meant to be like for tens or hundreds, but with the same sort of instructions.
I would say. But what I notice is as it increases, as long as you use microscopic methods, it sort of is scalable to a large scale crowds. But if you're trying to maybe put in some very individualistic behavior, for example, maybe some disabled persons, etc., that is not something we focused on, but probably could be extended to something like that.
All right, nice. Okay, so we gonna quickly check if there's any other question. All right, so we jump into the third paper then. There's few questions for Tianqing and Ruishi here. Well, actually, I liked a lot this paper, right? I personally work a lot on this area too, so I have a few questions. First, in your related work, you talk about SMPL or simple, right? Which is nowadays standard for off-the-shelf skinning parametric characters. And actually, SMPL, the strength of SMPL is it already provides some sort of corrective blend shapes, right, to correct skinning artifacts. I was wondering if you compared the way SMPL was built. It was built by optimizing some many 3D scans, and then the method learned to avoid some candy wrap effects, for example. Which in the end your method also does. So I was wondering if you ever compared with SMPL or what are the differences? I mean, I know the difference are the way that you tackle the problem, right? But I was wondering what comments you have on that.
Okay, until now we didn't compare with SMPL, as I mentioned in the presentation, because the vertices of the number of vertices of SMPL character is all the same, but our aim is to learn the different number of vertices characters. So we didn't compare with it, but in the future, we would like to try to compare it with SMPL. Actually, now we are working on this experiment.
So I can imagine. I mean, I use SMPL a lot, right? So I know some details, but I can imagine creating a synthetic data set of SMPL with random topologies, and then you train your method with it, and then you test it, and then you see how it goes, right? That's I think that would be the bulletproof test, right? I understand that, and I understand that your method is aimed for this topology invariant thing, which is cool. This brings me to another question, which is, I saw that all of your results are dressed characters. So they are, of course, synthetic characters, they're dressed. But I found it a slightly either misleading or I didn't quite get it. But the way my elbow deforms, it depends on what I'm wearing, right? Like if I wear a more loose jacket, it would deform differently than a more tight sleeve, right? So is this, I guess, is something you don't take into account, but I was wondering about that.
Yeah, now currently our work is not focused on the character who wear the loose clothes, but
well, some of the characters are wearing like a fairly losing clothes. They're not naked, right? So you solve this candy wrap effect nicely, but you don't reproduce the expected, let's say, garment or clothing deformation. I understand.
Yeah, I see. I will try. How to say? I think to train different. I noticed that in your lab that you have already done a work about a character who fit differently with the
yes, I mean I know a little bit about the topic, right?
Yeah. I noticed that maybe we will also try that the experiment to train the characters with different types of clothes or different materials or something like this.
But actually, I was wondering because so imagine that you have two different characters on the same pose, but the character is wearing something different. So then your training examples for the same pose would have the same deformation here or a different deformation. Like your ground truth values would be completely equivalent for different characters, or that would be slightly different?
Actually, now our ground truth data is firstly automatically scanned by mixed armor first, and then for some inaccurate deformations with some obvious artifact, we manually fix it with the post-space deformation.
I see.
Yeah. So,
okay, so but in reality, your method does not take into account any clothing. So it would be like naked characters or undressed characters and then you solve the skinning problems.
Yeah. We will do it in the future.
Yeah, nice. It's good.
Thank you for your advice.
And then I was wondering, actually, I really like this attention network. Actually, we're looking a bit into it too. So I was wondering, on your training data, do you randomize like the orientation of the characters? Because, for example, the same pose when I'm looking forward or the same pose when I'm looking that direction, like the vertex information is different, right? So how do you take all these into account, or you basically just have a lot of data for all the possible orientations of the character?
So currently the amount of our post-training data is very large. That about each character has about 8,500 random training poses, and now it can cover all the spatial transformations in our current test.
So for the same pose, you have different orientations for the same pose? Like if I'm a pose like this, do you have a training pose for this and then another one for that? Like that's human. That is exactly the same pose, but oriented differently?
Yeah, the orange is different, but it is the.
Yeah, you could probably. I'm thinking of normalizing this data. Maybe you simplify a little bit the data, but I guess we can follow up follow the conversation offline. I mean, it's a topic I'm really interested. Okay, I think we're running a little bit late, so we leave it here. I want to thank all the presenters who produced videos and papers, and we had a nice discussion with them. We're gonna have a short break, maybe it's likely 5 minutes or so, and then we're gonna go. We're gonna be back here for the next session. So stay tuned and don't leave. And see you soon. Bye.
Hey everyone, welcome to the 7th paper session at I3D 2020. It is titled Capturing the Real World. My name is Anshul and I'm a research scientist at Facebook Reality Labs. We have the authors of 4 exciting papers here to talk about their work today. The presentations are recorded, but they are here for Q&A and related discussion. Since we are running a little bit behind schedule, I will quickly introduce all of the speakers, after which the stream will play their recorded presentations. Once all of the presentations are finished, we will begin the Q&A session based on the questions in the various chat comments. So without further delay, let me introduce with the first paper in our session titled Real-Time Face Video Swapping from a Single Portrait. The authors of this paper are Luming Ma and Zhigeng Deng. Our speaker Luming received his PhD in 2020 from the University of Houston under the supervision of Professor Zhigeng Deng. Their research interest was real-time face reconstruction and manipulation from video. This summer, they joined FRL to work on face tracking in AR and VR. The speaker notes that the current work was built on top of their previous work, Real-Time Hierarchical Facial Performance Capture, published in I3D 2019. Our second paper today will be image-based rendering of cars using semantic labels and approximate reflection flow. The authors of this paper are Simon Rodriguez, Siddhant Prakash, Peter Hedman, and George Tetrakis. Simon, who will be presenting the paper, recently obtained his PhD from University Côte d'Azur in France, working under the supervision of George Tetrakis in the Graph Deco team at Inria. He's interested in real-time rendering, image-based techniques, and the extraction and synthesis of reflective effects. Our third paper today is titled Pass-Through Plus, Real-Time Stereoscopic Video Synthesis for Mobile Mixed Reality. The authors are Gaurav Chaurasia, Arthur Newwood, Alexandrugan Ichim, Richard Zaleski, and Alexander Sorkin-Hornen. Gaurav is an engineer in the Mixed Reality Group at Facebook Zurich. He works on real-time environment understanding for VR use cases. His main research interests involve novel view synthesis, 3D reconstruction, and high-performance computation, especially in the context of GPUs and mobile devices. And the final paper in our session is titled Repurposing a Relighting Network for Realistic Compositions of Captured Scenes. The authors are Baptiste Nicolet, Julien Philippe, and George Tetrakis. Baptiste, the main author of this paper, will present the talk. Co-author Julien Philippe will also attend to answer questions concerning his relighting paper, which this work is largely based on. Baptiste was a master's student at Telecom Paris at the time of publication and is now starting a PhD at EPFL. Julien is defending his PhD at the end of this month and is currently open for employment opportunities in Europe. So let's quickly start the papers, but remember the Q&A session for all the papers will happen after the talks in a sort of a panel format so that all of us can take part in the discussion. And so for questions, please use Discord and YouTube comments. And make sure you specify the paper and the author with your question. Without much further delay, let's proceed with the presentations.
Hi everyone, I'm Luming Ma. I'm going to present our work, Real-Time Face Video Swapping from a Single Portrait. In this work, we propose a method to photorealistically swap the faces from videos. The face swapping technique has attracted a lot of attention recently, since people have used it to forge fake videos on the internet. A well-known method is deepfakes. Here's an example. The left side is the original video. The right side is the forged video with face replaced.
I'm sorry, Lester. This is going so well. It's going exactly how I'd always dreamed.
The background and the facial performance are untouched, while the face identity is swapped by another identity. The deepfakes is a popular deep learning-based method. It trains 2 variational autoencoders. By switching the decoder, they can generate a new face image of another person in the same expression. Compared to our method, this method requires a large dataset of the 2 subjects, and it cannot handle high-resolution videos. Cyclogan can also be used in this scenario. Similar to deepfakes, it trains two generators and discriminators to ensure the generated faces cannot be distinguished from the real faces. But again, the result is blurry and unrealistic. Face swap is a model-based method, similar to ours. They also track a 3D face model, but their result is not temporally smooth. The main challenges in this problem is that many deep learning-based methods need very large training data, which is only applicable to celebrities. It's also very hard to make the swapped face temporally stable. And high-resolution faces are very challenging. We propose a real-time method to swap the face from a single portrait image to the target video in high fidelity. Our method does not need any training data of the two subjects. The generated video is temporally consistent and it keeps the source face features such as face shape. We first capture the face parameters from both the image and the video frames. Then we predict the geometry of the source face in the target facial expression, harmonize the appearance, render the source face, and blend the result into the target video. We employ a real-time face capture method to reconstruct facial expression, wrinkle dynamics, and albedo texture from both the source image and the target video. We use the local binary feature-based regression method to automatically detect 73 landmarks on the input image. We predefine corresponding vertices on the face model. The vertices are projected on the image using the pinhole camera model. We minimize the distance between the detected landmarks and the projected vertices to optimize the camera parameters pi, r, t, and the face model parameters WID and WEXP. After the optimization, we will have a coarse face mesh that is closely aligned to the input face. Next, we simulate the lighting with spherical harmonics and synthesize a colored face image. The table shows the evaluation of spherical harmonics functions for the first 3 degrees. By minimizing the distance to the input face image in color space, we solve the unknown albedo rho, weights of spherical harmonics G, and the normal vector N. After the reconstruction, we have the facial expression, identity, appearance, head pose, and the illumination. Our face swapping will change the identity parameter and the appearance while preserving the original expression, head pose, and the illumination. When swapping the face mesh, we want to keep the shape of the source face and animate it in the target expression. So the coarse mesh is computed as the bilinear face prior C multiply the source identity parameter and target expression parameter. In addition, we want to predict wrinkle motions such that in the target expression, the source face still has plausible person-specific wrinkle style. So the fine-scale mesh equals the coarse mesh plus the Laplacian coating of the source mesh plus the Laplacian coating deformation of the target mesh multiplied by the head rotation. The Laplacian coating deformation is the difference between the Laplacian coating at a frame I to the first frame 0. In the rightmost image, the predicted source mesh keeps its wrinkle in the target expression. For appearance swapping, we first do an albedo adaptation. The source and target faces may have different colors. We need to adapt source face color to target face color in order to blend it into target video without seams. This needs to solve a Poisson equation. The gradient of the adapted appearance needs to be close to the source face gradient, and the boundary color needs to be close to the target face boundary. Another potential issue is that the source face and target video are taken by different cameras. The noise pattern might be quite different. We do a histogram matching on the noise to harmonize the source appearance with the target image background. In the composition step, we render the predicted mesh, adapted albedo, with the target head pose, camera parameters, and lighting. Since the shape of the source face may be quite different to the target shape, simply overlaying the rendered face on top of the video might cause artifacts. As shown in the red rectangle, the ears are covered because the source face is much wider. So we perform triangulation using the facial landmarks on the target image and warp the image according to the rendered face shape. As shown in the green rectangle, after background warping, they match perfectly. Let's see some results. In this experiment, we can see that the face shape in the video is also changed to be the same as the source face, which cannot be handled in previous methods. The wrinkles on Obama face are lost because the source face does not have an obvious wrinkle style. We compare with face swap, which is also a face tracking based method. Our method is much stabler than theirs. Deepfakes and Nurkin et al. Are two deep learning based methods. The deepfakes result is low resolution. It is the limitation of variational autoencoder, even though we train the model on high resolution data. Nurkin's method is quite unstable, while our result is temporally stable and high resolution. The limitations of our method is we cannot swap hair, eyes, or mouth interior. And it's very difficult to separate identity and expression. For example, if the source image shows oblique eyebrows, there are two possibilities. The subject has oblique eyebrows and makes a neutral expression, or the subject has flat eyebrows but makes oblique eyebrow expressions. It is very difficult to distinguish between the two possibilities, even for humans. If our method reconstructs the face with oblique eyebrows in the neutral expression, the oblique eyebrows identity feature will persist in the whole rendered video. Otherwise, the oblique eyebrows expression will be replaced by the target expression such that the rendered video will not have this facial feature anymore. To overcome this limitation, we can use a collection of images of the source face to estimate a more accurate and robust identity. To conclude, in this work, we contribute an automatic real-time system to swap the face in an RGB video by the face from a single portrait image without any training data. Our method can preserve the face shape, which is not considered in previous methods. Our method can also predict wrinkle dynamics of the source face in target expressions. And we contribute an appearance harmonization method to video realistically blend the synthesized face into the target video. Thank you.
Hello, I'm Simon Rodriguez from the GraphDeco team at Inria, and I'm going to present our work on image-based rendering of cars using semantic labels and approximate reflection flow. Being able to virtually explore real-world urban environments has many applications, from mapping and guidance to training data generation for learning to automotive testing. To provide realistic exploration, replicating entire streets manually would be long and expensive. Photogrammetry can be used instead, where hundreds of pictures of the scene are captured and used to extract the geometry using multi-view stereo on the input images. This geometry can then be used to render a novel view using a texture or input image information. This is a complex problem, as streets exhibit many adversarial elements. Among them, cars are omnipresent. They are difficult because they present both reflective and semi-transparent surfaces that break multi-view stereo assumptions. This means the reconstruction will have many artifacts and missing elements, as shown here, artifacts that propagate to rendering, whether you're using a textured mesh or image-based techniques. We wanted to tackle this specific problem, and we realized that there is another task that has been applied a lot on street scenes, and that is semantic labeling. We thus tried to leverage semantic data to improve our reconstruction and rendering process, still focusing on cars. To be able to provide interactive exploration, we need three things. We need to improve the car geometry and recover the windows. We need to be able to generate reflections when the user moves around the street using our input image data. And this requires us to separate reflection information from the background and the transmitted interior in the input images. Existing methods have considered the problem of reflection and transparency rendering from real-world pictures, such as the work by Sina and colleagues and Kopf and colleagues. But these works were mainly demonstrated on planar reflectors and for small user motion. More recently, neural-based techniques have been applied to a similar problem, for instance by Mildenhall and colleagues, but once again with a denser baseline and a more constrained capture setup. Finally, we will take inspiration from classical approaches when extracting reflection information, such as the work of Zelinsky and colleagues. I'm now going to provide additional details on our approach. We start by capturing pictures. To simplify this step, we use a GoPro device in burst mode and move around each car in the street we want to capture. The process takes at most 10 minutes per car, and we get around 250 images for each car. Each image is labeled using an out-of-the-box segmentation neural network trained on car and car parts labels to obtain semantic maps. We estimate the camera locations and the global geometry using a classical multi-view stereo pipeline. Let's now focus on our first goal, improving the geometry. As shown on the top image, many parts of the car are missing. The windows and the roof, because they are either highly specular, transparent, or seen at a grazing angle. The first thing we want to do is to be able to isolate each car from the global mesh. For this, we reproject semantic labels from input views to the mesh to obtain a multi-view consensus and extract the car. we now want to refine the geometry of each car and fill, for instance, missing surfaces. Because the car mesh is potentially noisy, with multiple components and spurious geometry, we move to a more appropriate 2D space for refinement. We project the car onto a bounding sphere, generating a fisheye-like depth map. This choice of parameterization allows us to refine the depth map using standard 2D operations, such as Poisson filling. We can also reproject the semantic labels in the same space and use them to detect which regions should be filled. We perform hole filling by solving a diffusion problem guided by the semantic map. Once the depth map is refined, we can update the semantic labels and iterate the process. Finally, the depth map is retransformed into a mesh with filled holes. We then symmetrize the mesh and split it into the hull, which will be reinserted in the global mesh, and the window panels that will be used as a support for rendering reflective effects. Now that we have cleaned up the geometry, we can render the scene. To handle view-dependent effects, we use image-based rendering. When generating a novel view, for each pixel, we use the geometry to find the corresponding pixels in the input images. In practice, we fetch from multiple close input views. This works well for diffuse and glossy surfaces because the appearance of the point on the car body is varying smoothly when moving around. But for mirror-like specular reflections, such as the windows, the flow of reflection when changing viewpoint is very different because it depends on the background point which is visible in the reflection. This means that at runtime, we need to be able to find the background point from the novel view and then find the input view pixel that shows the same background point reflected. Furthermore, we don't directly have the reflection information available in the input views. We have the final blend of reflection and transmission, and we will need to separate them. I'm now going to give more details on the way we compute the reflection flow. This is a complex task that requires multiple simplifications. First, we need a representation of the background which can easily be queried at runtime. For our case, we use a bounding sphere of the scene, because the background is far away on the other side of the street. We then need to find the reflection point for the input view, which is a non-invertible problem for arbitrary reflectors. Yet, we know how to qualify that reflection location. For a perfect mirror, this is a point where the bisector of the reflection path, here in green, and the surface normal, in red, are aligned. If we find that point, we can reproject it in the input view and fetch the corresponding information to render the reflections. But how do we find that point? We need to search on the surface, but it's hard for arbitrary surfaces, and this is not necessarily a bijective problem. In practice, we search on the surface using a gradient ascent, trying to maximize the alignment between the two vectors. Based on the misalignment, we can update the position on the surface and iterate until convergence. To be able to do this in real time without extra data, we have to simplify our reflectors and rely on an analytical representation. We use an ellipsoid because this is a compact representation and it has interesting properties for our problem. We want to represent each window as an ellipsoid. We use the windows extracted from the initial geometry as a support to locate the windows in the scene and orient them. We then need to find the remaining parameters of the ellipsoid, the radii. To find the best set of radii, we sample a range of plausible values and pick the set that allows us to warp between input views accurately using our flow computation. This is evaluated by automatically matching reflection features between neighboring images. For each window, we obtain a fitted ellipsoid. we can now compute the flow of the reflections. But once again, we can't just fetch information from the input images because they contain a mix of reflection and transmission. We thus need to synthesize a reflection layer. We rely on a standard mean composite approach to separate specular effects from the rest, using our flow computation to compare neighboring images. The result exhibits ghosting artifacts and harmonization issue, and it is thus additionally refined and harmonized to minimize this. This is done as a preprocess for each input image, and we obtain a set of reflection layers. We can also generate transmitted layers by averaging input images, which will be useful for the interior of the cars. To summarize, we now have a cleaned-up background and car hull that we can render using classic image-based rendering techniques, such as the unstructured lumograph or deep blending. The interior of the car that we will also render using image-based rendering and our transmitted layers. Finally, the reflections that we will render using the extracted windows as support and our ellipsoid representation to compute where to fetch in the extracted reflection layers. I'm now going to present some results. We compare two multiple image-based rendering techniques. Each time, the input and current cameras will be displayed in inset. More extensive comparisons can be found on the project webpage. Please notice how reflections shift when moving around the car. We first compare to a textured mesh. Because we refine the geometry and use a more complex rendering approach, the difference is quite clear. Once again, you can see how the reflections are moving on the surface of the car windows. Here, we compare to the unstructured lumograph, which relies on the global geometry and thus suffer from missing surfaces when rendering reflective elements. We also compare to the same background technique we are using, deep blending, which here is unable to properly render reflections as their flow is different from the regular diffuse geometry flow. Finally, we compare to a recent volumetric approach that is able to capture transparency effects, but does not handle other surfaces as well. We also support interactive sessions, here using deep blending for the background and our technique for rendering the car interior and the reflections on the car windows. We currently have some limitations and opportunities for future work. While we process the outer hull of the car, the interior often suffers from very low visibility in the input images and is often very noisy and imprecise as a result. The layer separation is an approximation that can sometimes introduce extra ghosting of transmitted elements. Finally, generalizing the reflection flow computation to more complex reflectors would be an interesting avenue for future work. To summarize, we have presented a method for realistic rendering of real-world streets by improving the reconstruction and rendering of adversarial elements, cars. We refine their geometry by leveraging their topology. We estimate an approximate reflector representation that can be used to warp information between the input views and the novel view at render time, which is combined with a pre-process extraction of reflections from the input views. Thank you for your attention. I'll be happy to answer your questions during the discussion session.
A very good day to all the viewers. My name is Gaurav and I will present our work on Pass-Through Plus, an approach for view synthesis for VR devices. Light fields was one of the first view synthesis techniques more than 2 decades back. Since then, view synthesis has been explored and improved in various contexts. In a recent paper, for example, researchers have explored how to handle arbitrarily complex scenes and even specular effects. Our work focuses on view synthesis to enable an immersive first-person viewing experience. It is designed for mobiles and VR devices and is available to users on Oculus Quest. I will first explain how our work is used on Oculus Quest headsets to highlight the problem statement and then dive into the details of the technique. Here we see a first-person video of a user looking through their VR headset. Our approach allows the user to see their room and mark a safe region. After marking the safe region, users can go inside and experience VR content. As soon as they walk out of the safe region, they are transported back to their room. Our approach thus allows a user to see their real world while wearing a VR headset. Why is this a view synthesis problem? That's because the capture cameras on VR headsets, which are shown in blue, do not coincide with eye view, which is shown in orange. Thus, we need to synthesize eye views from the captured images. A naive projection of captured images without accounting for scene geometry to the eye views would lead to artifacts and motion sickness. Standard approach for view synthesis is to use 3D geometry in a 3-stage pipeline. The first stage computes the 3D reconstruction from input images. This can be stereo matching if the input is a stereo pair, or multi-view stereo or depth sensing. This is typically done as a pre-processing step. At runtime, the geometry is warped to novel view, and this gives a representation of the scene in the novel view. Finally, the warped geometry is textured using content from one or more input images. Our approach to view synthesis has the same outline, but our use case throws a number of challenges. First of all, we cannot pre-compute the 3D reconstruction. We get new images of the dynamic scene at camera rate, which is typically 30 Hz, and we need to compute the 3D geometry on the fly. Moreover, this has to be highly efficient, both in terms of computation time and also in terms of power, because the target is VR devices. Next, our geometry, when warped to the novel view, must produce an immersive and smooth experience. It should not have artifacts like high-frequency temporal noise. And the final result has to be rendered at display rate in a stereoscopic fashion. We start with 3D reconstruction. Since our input is a stereo pair, we could use any stereo technique from literature. However, stereo matching is a compute-intensive step, irrespective of the algorithm used. Our main insight is to replace stereo matching with a video encoder. Encoders are designed to estimate flow fields between successive images, which are also called motion vectors. These run on much lower power as compared to CPUs on mobile devices. We use video encoders to compute motion vectors between stereo pairs. Encoders do not respect epipolar geometry. We alleviate this by adding an additional epipolar consistency check, which we will discuss in the subsequent slides. Also, we observe that the result can be noisy. We will explain an outlier suppression algorithm to alleviate this problem. The standard usage of a video encoder is to compute motion vectors from successive frames. These motion vectors are used for video compression. Instead of the standard pipeline, we feed the left and right images at the same timestamp to the video encoder and obtain motion vectors between them, which we transform to disparity values after an additional epipolar check. If you look at the full pipeline for 3D reconstruction, the standard approach is to estimate correspondences via stereo matching and then triangulate. As I mentioned, this has a relatively high compute and power cost. Instead, we feed the left and right images to the video encoder. The encoder returns a stream of motion vectors, which we decode on the CPU to extract the actual motion vector. We then check the motion vectors for epipolar consistency and reject those which fail the consistency check. We then apply an additional outlier suppression step, which we will discuss in subsequent slides. We then triangulate the inliers returned from the outlier suppression and obtain the 3D points. Our approach is more efficient than the standard approach for stereo matching, as we will see in the next slide. In terms of performance, we compare our approach to a stereo matching implementation that we optimized. We find that our encoder-based approach is slightly faster and uses less than half the power. Specifically, motion vector estimation on dedicated hardware is almost free in terms of power consumption. This is the main reason we have opted for this technique. We will look at evaluation of the quality of reconstruction at the end of the talk. We now look at the details of the outlier suppression algorithm because this was important for getting high quality results. We observed that the disparity values from the video encoder vary across time, leading to high frequency noise. In order to fix this, we maintain a set of prior points along with a vote for each point until time t-1. We project these points to frame t, which gives us a prior for frame t. We also have stereo points from time t, which are computed using the camera input at the same timestamp. We call these the observations. We check the observations against the prior. If they match, we advance them to the result with an incremented vote. If they do not match, we decrement their vote and assign them as priors for the next time. Thus, over time, the points which are observed repeatedly stay in the result set, while those which appear and disappear are never advanced to the result set. They remain in the prior set. This leads to a temporally stable result. Until now, we have a set of 3D points. We now try to convert it to a mesh which we can render afterwards. We can easily compute a depth map by projecting the points to a grid, but the depth map, which is computed in this way, has holes since the distribution of points is not uniform. Also, that the depth map does not cover the full field of view of the user because it only covers the field of view of input images. Thus, it will not give an immersive experience. In order to create a mesh, we first compute a 180-degree hemispherical grid around the user at some fixed depth, let's say 1 meter. We parameterize it by viewing angles as shown from -90 degrees to 90 degrees in both x and y direction. No matter what the depth value is, the grid will always show the full field of view to the user and give an immersive experience. We then project 3D points we computed earlier onto this grid and get some depth values for some of the vertices of this grid. The others are still unknown. We complete the depth map by propagating known depth values to all other grid vertices. For this, we solve the Laplace equation, whose data term is the set of depth samples we obtained earlier. The smoothness term is the Laplacian kernel. We observe that repeated convolutions with the Laplacian kernel solves this much faster than a direct linear solver. This observation is also used in fast image completion techniques. After the completion step, each vertex of the hemispherical grid has a valid depth value. We thus have a full field of view mesh that aligns with scene geometry as shown here. We now render this mesh for both left and right eyes by using standard rasterization. After rasterizing the grid into the left and right eye views, we use the left image to texture the left eye and right image to texture the right eye. This minimizes occlusion artifacts since the baseline between texture source and eye view is smaller. We do not blend left and right eye images since it led to ghosting artifacts. In this video, we can see a user walking around using our approach to see the room. As you can see, the renderings are smooth, the user is able to walk around and also interact with objects. This is what our approach was designed for. You can experience this too on an Oculus Quest headset. Our total computation time is less than 9 milliseconds. Therefore, we can refresh the geometry at camera rate, which is 30 Hz. It is important to refresh the geometry at high frame rates to ensure that the user has a comfortable experience while looking at dynamic scenes. Our total rendering time is less than 4 milliseconds. This allows us to render both left and right eye each at a high frame rate of 72 Hz. This is important to ensure a smooth visual experience without any frame drops. We evaluated our 3D reconstruction by comparing to ground truth datasets. We captured 450 datasets using laser scans. These are accurate up to 1 mm. We then compared our depth maps to these scans and observed a 1 to 4 cm error in a 1 to 2 meter range. We observed a higher error for closer objects because the disparity in these regions is way too high for the video encoder to estimate correctly. Note that these error values are worse than state-of-the-art stereo matching algorithms. However, our goal is to deliver a smooth and plausible viewing experience rather than a highly accurate 3D reconstruction. Rendering quality is hard to evaluate since we do not have reliable perceptual metrics. This is an area of future work. In conclusion, we have presented a view synthesis approach that allows users to experience immersive mixed reality. Our solution is low power and low latency. It is built on top of 3D reconstruction and depth map completion, which are designed specifically for this use case. Aside from performance, our system focuses on providing a smooth viewing experience by suppressing outliers over time. As future work, we would like to improve the reconstruction and rendering quality for nearby objects. We would also like to work on perceptual metrics to evaluate the quality of rendering from our system. With this, I would conclude my talk and thank everyone for the attention. We're always looking for individuals who want to push the boundaries of machine learning and computer vision to improve augmented or mixed reality experiences. If you're interested, please contact us. Thank you.
Hello everyone, my name is Baptiste Nicolet and welcome to this virtual presentation. In this talk, I will present a joint work with Julien Philippe and Georges Dretakis at Inria Sophia Antipolis in France, which is a method for creating realistic compositions of scenes captured with photographs. Let me illustrate. If we have captures of scenes with photographs, such as here Chichen Itza in Mexico, and maybe here Stonehenge, what we may want to do is extract parts of one scene and import it into the other like so, to create a new original composition. But simply copying and pasting it into the other scene results in poor realism, mostly because the two scenes were captured in different lighting conditions, so the existing shadows are misplaced, as you can see here, and also the object does not cast shadows on the ground here, as it should. We propose a method to improve the realism of such compositions by generating a coherent lighting, as you can see here. But first, let's back up a bit and see how we create these compositions in the first place. In common graphics pipelines, we rely on physically based rendering, or PBR, where light paths are simulated in a scene, and this allows for realistic renders and very fine tuning of the final appearance of the scene. However, rendering is quite expensive, and creating complex scenes often requires several artists working on them for weeks. And on the other hand, image-based rendering, or IBR, relies on photographs of a scene. The geometry is extracted from these photographs using computer vision methods, and then both photographs and geometry are leveraged in the rendering algorithm in order to generate a novel viewpoint. And this allows for real-time free viewpoint navigation in the scene. And since the illumination and geometry are computed for free in the input photographs, this allows for real-time realistic rendering and also for a very fast creation process for complex scenes, as it only requires taking several tens of photographs for the user. So in a day, one may generate a scene that could take weeks to generate using PBR. However, the fact that everything is computed in the photographs also means that tweaking the appearance of the final render is quite difficult. And using IBR, we can generate this image, this composition, And this illustrates quite well the drawback of IBR. Since everything is computed in the photographs, lighting is very inconsistent here, as I explained before. Now, there has been some work on editing scenes captured with photographs, but they mostly focused on duplicating, moving, or removing objects in the scene. And they usually don't tackle the lighting issue, or they do so in very specific contexts, such as virtual real estate visits. Now, the recent work that's closest to what we want to achieve is the work of Thies and colleagues in 2019, in which they used a neural rendering approach in order to duplicate objects in a scene. However, they do not handle lighting, and we'll compare our results to theirs later. Now, in order to achieve these results, we need to change in some way the lighting of the scene. Fortunately, image relighting has been a very popular research topic, especially with the recent advances in deep learning. There are several methods that either use single images or multi-view datasets. For our work, we will use the network designed by Philippe and colleagues in 2019 in order to generate coherent lighting. So now let's see how we can use this network in our context. This is a geometry-aware network, which means that it relies on the geometric information for prediction. We know the source sun position and define a target one. And we can use the geometry to create shadow masks. And these are then fed to the network alongside with the image to relight and also the geometry information in order to produce the relate image. And this network produces very high quality results for outdoor scenes. Now, let's go back to our problem. We have a first scene in which we import an object extracted from another one. If we feed this image directly to the relighting network, this is what we get. As you can see, we get already quite a boost in realism, mainly thanks to the shadow the statue casts on the ground and the wall. But this is very far from perfect. The original shadows are not properly removed, and this is caused by the fact that the network was not trained to deal with inconsistencies in sun positions, as it is the case here, and thus making it fail. On top of that, it was trained with synthetic data, using physically based rendering scenes for ground truth, and the IBR scenes created from these PBR scenes. So we decided to use another approach. We use the network off the shelf and use a deferred approach. In order to stay in the single scene context the network was trained for, we first rely all scenes individually to align the sun positions, and then we relight the final composition in order to generate proper interaction between the parts of the scenes. So from this image, we get here after the first step of our approach. Here, both the statue and the runes are lit from the same sun position. And if we feed that once more to the network, this is the second step, we get the proper cast shadows. And this approach allows for much better shadow removal compared to directly using the network. Once we have coherent lighting, we apply a couple tweaks to improve the realism of our results. So the first one is to provide the user with control over color temperature of each object. And we do this because scenes may have been captured with different cameras and different camera parameters, and therefore the white balance may differ from one object to another in the composition, and that can be quite noticeable. So changing color temperature allows to quickly compensate that. And this is the result. Now the second step is to compute the ambient occlusion in both the composition and the original scenes, and this gives us a per pixel ratio that we can apply to our image, and thus allowing to visualize better the new contact points, such as here, between the base of the statue and the ground. So now that we have detailed our pipeline, let's take a look at some results. Here we imported two statues into one scene, and this is the result using our method. And here is the result using an arbitrary target sun position. So as you can see, we can use any target sun position with our method. And this is another result using the original sun position as target sun position. And this is what we get using the neural rendering approach by Thies and colleagues in 2019 after around 12 hours of training. As you can see, this is pretty close to simply copying and pasting the object in the scene, since there are no cast shadows on the ground, and the self-shadowing is also wrong because we rotated the object, so it is not lit from the same direction as it was originally. Now, using our method, we can also relight all the images in our multi-view scene in order to generate a new IBR scene, and thus allowing us for real-time free viewpoint navigation in the composition, as you can see in this video. This is the original scene, and this is the relit scene. This is the same thing with another scene. And here we add an object, run our relighting, and this is the results. Now, while our methods has some very satisfying results, especially since it's the first method to tackle this problem, it also has some limitations. The geometry extracted from the photograph is imperfect, and that leads to artifacts. Here, as you can see, part of the sky is reprojected on the tree due to over-reconstruction of the tree. And this is even exacerbated when using our method, as we added this wall behind. This is very noticeable and unrealistic. Also, the network is only able to generate shadows that are cast by the geometry. And as a result, fine shadows caused by small details in the geometry that are not in the reconstructed geometry will not be synthesized. As here, you can see there are small bricks casting very fine shadows, which are not in the geometric proxy. And so they are not synthesized by the network and giving it this sort of smooth appearance. And the main drawback of our method is its performance. The first step of our deferred approach can take up to 10 minutes on large scenes, and after that, the second step can only run at a few frames per second. So to sum up, in this work, we introduced the first method in order to quickly generate compositions of scenes captured with photographs by repurposing a relighting network using a deferred approach. In the future, we are interested in improving the performance of our method, starting with an optics implementation. We are also interested in using more recent image-based rendering algorithms such as deep blending, which is the state-of-the-art by Hedman and colleagues in 2018. And we're also interested in exploring more complex lighting models such as indoor scenes. So that's it for me. Thank you for listening. And if you have any questions, I'd be happy to answer them.
Thank you to all the speakers. Those were some wonderful talks. Great learning experience for me. And it was great to see so many good pieces of research on sort of this topic at I3D. I was also sort of really happy to see sort of the occasional overlap between the topics and the problems and the solutions presented. So that was pretty cool. I encourage everyone to go read the papers that are associated with this work, especially for all the cool details and places where the bodies are buried. All right, now we are at the Q&A stage of this process, and we will go through the questions for each paper, try to take them from the various chat sources, and then discuss with the authors. And even though the questions would be for some specific paper or some specific author, I encourage all the authors to chime in with their thoughts about the topic, since there is quite a bit of overlap. So I will start with one question that I've seen in Discord. This is for Gaurav. The question is, were just the same two cameras used for stereo reconstruction, or did you try mixing the cameras for input? And how, if you did that, how might that change the power requirements of the approach? So I believe they're talking about all of the other cameras that you have on Quest, and how many and which did you use for which eye?
Right. So the choice of which two cameras to use for reconstruction was motivated simply by how much overlap they have. The cameras which have the most overlap are most likely to give us the best reconstruction. We did try to mix different cameras. It did not lead to any noticeable change in power estimates. So we stuck to the 2 cameras, which gave us the best in terms of stereo overlap, as well as overlap with the field of view that the user is supposed to see. For the use case, we more focus on looking at the lower part of your field of view, because you want to look at obstacles and such, and not the roof. So we focused on the lower cameras. But that was the only reason. We tried using all 4 cameras, but it did not buy us significantly more in terms of, it improves the reconstruction quite a bit. That's absolutely true. But the increase, it almost doubles the power estimates and did not improve the visual quality that much. So we stuck to the lower 2 cameras.
That makes sense. And these are all grayscale cameras, right? So you're not going to get any color information from them. Okay. Okay. I have some questions of my own for each of the papers, so I think I will just kind of start to walk through them as the YouTube stream catches up and people ask more questions along the way. So for the first paper, question I have is, how do you measure for the face swapping algorithm? How do you measure success, right? Like, how do you measure whether you've done a good job? Because these are kind of sort of a algorithm that is some of a creative source, right? You're trying to produce something that probably doesn't really exist. So how do you measure how well you've done? And is there a way to set up some sort of test or validation that would help go further there?
Yeah, thanks. That's a great question. So for this face swapping, it is really hard to do like qualitative evaluation. So in our experiments, what I did is we do a self-swapping. So like the source image and the target video are taken from the same subject, and then we swap the same identity into the video and like measure the photometric distance between the original video and the rendered video, so that we can calculate the difference. And the result is presented in the paper. So the area is pretty reasonable in our experiments. And other than that, we largely rely on qualitative evaluation.
Mm-hmm. That makes sense. So just to clarify, you take a video and you take one of the frames of the video as the source for the swapping,
right?
And then measure how it should not make any difference to the video, and you measure how much difference it does make.
Yeah, ideally that should be the same, but in reality we couldn't have exactly the same results.
Right, that makes sense. Did you try picking a different photograph of the same subject, like and then trying to map that same face from a different photograph or a different video to a video of the same subject, right? Let's say you had Hillary Clinton, let's say a photograph of Hillary Clinton from some random video, and then a video of Hillary Clinton, swapping that face. Is that worse, better, or have you tried it?
Yeah, I think it didn't get worse because what I did is I pick a frame from a random Obama video and swap it into another Obama video, and the result is very similar to pick the frame from the target video.
Mm-hmm. That makes sense. If it's very similar, that's actually quite encouraging about this work. That's pretty cool. Another question I have, and by the way, other authors, please free to chime in if you have follow-up questions or points to add to what Lu Ming's just said. I have sort of an inverse and sort of philosophical question. What are some of the giveaways or telltale signs that your algorithm has been used to swap a face? And this is obviously for some of the use cases of this algorithm that could be questionable and maybe important to recognize whether something like this has been used. So have you thought about that? Did any work on that so far?
I didn't. That's a really good question. So there's some ethnic issues or discussions in the community, like is it legal to swap face? So there are more and more researchers working on to automatically detect the forged video. So my research just focus on the generation of this, or focus on the technical part, but I didn't think of too much application. So one would be like we can use that in the movie industry, so we can swap the face for actor if the shot is very dangerous, so we can put him in a safe place and swap the face and as post-processing. And so yeah, that's what I have right now.
Makes sense. I was just curious if you have done any experiments to that, or are you aware of the final image is like a little bit more blurry, or it has some artifacts that kind of are not present in the previous image? But anyway, we can take that offline, and the viewers should feel free to ask questions in the various chat channels if they have follow-up on this topic. Let me move on to the next paper, which is image-based rendering of cars using semantic labels and approximate reflection flow. So one of the questions I have is that I've seen some recent work in the area of neural novel view synthesis that attempts to and does a reasonably good job at reproducing reflections and glossy surfaces. I'm specifically talking about MPI, MSI-based representations, or even NERF-based representations that have presented some promising results in the area of capturing and reproducing reflections. So do you have intuition of how they might, what are the limitations of those work compared to yours, or vice versa?
So usually the neural approaches rely on either having a more structured capture on a regular grid on both dimensions, for instance, right? Capturing everything in a plane, for instance, or also rely on having a very high number of cameras to be able to train and build the scene representation. Mm-hmm. Which means that, yes, usually the capture setup can be more complex than in our case, especially as this is something we focused on trying to simplify the capture process as much as possible. So I think that might be one of the differences here, right? That the capture has to be more controlled for those methods.
Mm-hmm. That makes sense. That makes perfect sense. That's a good answer. Another question I have is regarding if you wanted to, and this is again sort of me looking at sort of other literature that I've seen in this area. What would be some of the challenges if you had to upgrade your work to work on videos of, let's say, a moving car or an environment that is moving with pedestrians and so on? What would be the challenges of reproducing like the reflective objects there?
So that's a very interesting question, especially as presented, we rely on the geometry of the scene quite a lot. So for a video, right, we would have to be able to build the geometry for each frame and ensure that our refined car can be used for the whole video to provide consistency, right? So that would mean a way to be able to either build an initial representation, extract the car, refine it, and then be able to re-inject this refined car in the geometry of each frame. Same for the windows themselves, right? This also raises interesting questions in terms of extracting the specular information from the input images. Even if, you can always consider a set of frames as just input images in that case, I would say. So I think, yes, the geometry might be what would need the most work in terms of ensuring the consistency, because here also like a single video would provide probably a lower amount of information on the scene, in the sense that we still need to be able to capture at different elevations, for instance, to really be able to extract all the specular effects on the car windows.
Right, that makes sense. And if the car is moving or the environment is changing, do you anticipate any concerns with the temporal stability? I know that in the current implementation, it's really good with respect to being consistent frame over frame, but would that change if the environment is dynamic?
So for the windows themselves, probably not, because once the representation is built and the layers are extracted, this is a quite stable. I mean, the representation is stable, and the algorithm for solving the reflection flow would not suffer, I think, from general motion. For the background technique, then it remains to be seen. Different background techniques will have different stability in that kind of setup, I think.
That makes sense. Yeah, thank you so much. All right, let's move on to the next paper for now. And I have a question for that paper for Gaurav. So what is the path in terms of what are the biggest research challenges of taking something that you've built into a fully immersive AR-like experience, right? Where there's, people can kind of stay there for a longer amount of time, interact with objects for, not just to get back into VR, but kind of stay there and be productive or be play a game or something like that. What are some of the challenges that are the highest priority for that kind of path? I believe you're muted.
Every time. So there are 2 or 3 different types of challenges. First are just ergonomic challenges, which are dependent on what kind of a device you're using, what's the quality of the cameras, what's the quality of the screen. So these are things that we can talk about at great length, but let's ignore those for the time being. The second big chunk of issues come up with people are very good at perceiving a temporal artifact. Even if spatial artifacts are not very visible, you can see distortions and all. But if things are varying temporally, that's just very easy to spot. This becomes a very big challenge because most view synthesis papers, they kind of work on one snapshot, and then we can move around the object, but the scene is kind of static for the duration of, for the purposes of the capture. In a VR or an AR application, or an immersive experience, the scene is constantly changing. So you have to come up with a temporally stable representation, geometrically as well as from a rendering perspective. That's the second big challenge. The third big challenge is simply, it's very difficult to describe it, but you get motion sickness or you get all the perceptual problems that you see in VR applications. You have the divergence accommodation conflict, you get motion sickness, all of these hit you at the same time. So it's somewhat difficult to build an experience where you can stay for an extended period of time. Any latencies that you induce into your computation pipeline, it's not, as a user, you wouldn't know that something is not very fast or something is lagging behind, but it will give you a headache very quickly. So it's very hard to quantify that. As a researcher, it's hard to quantify these things. And then actually try to show that we've actually improved these or we have regressed on any of these fronts. So I think that's one of the biggest challenges. That's the last challenge, I would say. Purely from a research perspective, how do you evaluate if you have made progress or not?
Yeah, that makes good sense. And so does it only work on like a VR headset at the moment, or does it also work on an arbitrary, like an Android cell phone or some sort?
So this is from a algorithmic perspective, it'll work easily on a phone. It'll probably work a little bit more easily on a phone because your constraints, like the stereoscopic constraints, are not there. Makes it also easier to have artifacts and not notice them in the final rendering quality. So it's not tied to a particular headset or a particular kind of hardware. However, as our paper mentions, a number of algorithmic choices are very hardware-centric because we want to hit the latency bars and the power estimation bars. So those don't transfer very easily across hardware. As soon as you move to a different hardware, all of these numbers will change, and some of them may become a breaking issue. the algorithmic ideas, they transfer well. For Oculus headsets, we have the Rift, which is a Windows-based device, which has a very similar experience that you can use there, and that is powered by NVIDIA's optical flow. So the ideas are all there. With different hardware come different challenges.
That makes perfect sense. Yeah, thanks for those answers. All right, let's move to the final paper of the session, repurposing a lighting network for realistic compositions of captured scenes. I'll get questions for Baptiste and Julien. So these are both my questions. I'll ask you the first one. So I was unsure if it was clear in the talk, but what fidelity of representation do you use for your inserted objects, or is there like a limit on that, or is it just limited by what you can capture and reconstruct? Like, can I put an artificial object in there?
Well, the method is really designed to import captured objects. So I'm not sure that there would really be a point in adding a synthetic object inside it. Plus, you would need to get really realistic lighting of this object, use a path tracer, and that would imply a significant overhead in the rendering. There are some methods that do that, including synthetic objects in photographs, but that wasn't really the scope of this paper. And really, there isn't much difference between the scene in which we import the objects and the scenes from which we extract the other objects. So it depends on the density of your capture and how many pictures you take, and you could take basically anything you want to. Yeah,
makes sense. That makes sense. Thanks. Another question I have is, again, I think a similar question to what I had with Simon. How can you evolve this work to insert, let's say, objects into videos or animated objects into videos? What would be the key challenges to go to that step?
Well, I suppose you could already use this method to animate some objects that you have captured in the scene. You would just need to run this relighting step for every frame. It could be quite expensive depending on what you do with this animation. Like if you rotate a whole object, then you would need to recompute the whole lighting of this scene from which you captured this object. So that could be expensive. Inserting into a video, well, I suppose a video is simply, depending on the video, if you take like a drone video, which is actually the example of Chichen Itza and Stonehenge, those are captures taken from drone videos. So if you relight it, you already have the relit scene. So you could just play back the video and use that. But otherwise, it could be a bit more complicated. Yes.
That makes sense. And you mentioned there's something about being expensive. Can you talk a little bit about the runtime performance of your approach, both the processing and the final rendering?
So we have a first pre-processing step, which takes under 10 minutes for scenes that count typically 100 to 200 images per scene, right? And that's on let's say a decent machine with a 1080 Ti GTX and 32 or 64 cores, and then if you want, you can run the second relighting step on in real time, and then it will run at between 2 and 5 frames per second. So it's enough for navigation, but it's not very fluid. And then if you want, you can relight all the input viewpoints. This would be quite a bit more expensive since you need to compute this ambient occlusion term.
with our experiments, it usually took between 20 and 30 minutes for the same scenes. And then once you have done that, you can simply run image-based rendering as you would do with a normal scene.
Got it. That makes sense. Yeah, thanks so much. Yeah, I don't see any more questions in the chat, but I mean, I have all the experts of this topic in front of me. So if you have questions for each other, I think now is your time to ask them.
Actually, I may have a question for Gaurav. I was wondering about the hands, because you mentioned the fact that very close objects may have issue because of the disparity. I was wondering for the hands, what's happening? Is it working well?
Hands are not the best things that work for us. They are the most challenging case. They usually are okay more than a distance of 30 centimeters, around 45 centimeter mark. But if you get closer than that, not only is the reconstruction bad, but also the rendering at that point is like the conflict you will see in, because you're very up close and the rendering is in the wrong place, your brain just cannot merge the two into a stereo image. So that becomes very uncomfortable. In terms of at more reasonable distances, like 45 centimeters odd, we get the highest amount of noise in terms of stereo reconstruction, because the disparity is the highest at that level, but still you can reconstruct it. So you get noise there. One of the biggest follow-up work we have is how do we stabilize reconstruction in the near field, which is less than 1 meter, while also keeping it high fidelity. So this is something that we're trying to improve.
Thanks.
That's great. More questions? Right. Well, if there are no more questions in the chat and no more questions in the video session, I would like to take this opportunity to thank all the speakers as well as the I3D organization for a very smoothly organized papers program in this particular session. So I'll clap that and hope all of you have a great day, and thank you so much for participating. And I think you're still able to ask questions in the Discord, and the authors can either hang around or keep checking that to provide answers offline. But if that's the end of this session, and thank you so much and have a great day to everyone.
Thanks, everyone. I'm just going to jump on. I'm Eric Haynes, the General Co-Chair for I3D 2020. And I just wanted to say, along with Dan Kessis, who you saw earlier today, thanks for showing up. We have a full program for you tomorrow. The day starts with a keynote by David Moran from Epic Games. It'll discuss in-camera visual effects, which have been used in Westworld and other productions. I want to make sure you know this talk will be only live streamed. There will be no permanent recording. His keynote will be followed by a long session about GPU techniques and data structures. After that, we'll have a town hall where registered attendees can give us feedback on how we can improve I3D conferences. We'll then wrap up with awards and goodbyes and maybe some gaming afterwards. Hope to see you tomorrow. Thanks for coming, and this ends our sessions for the day. Take care.